on vaccine immunology and development. Indeed, today we came to know that so much of thought process is going on for identifying the immunization system. I extend my thanks to Dr. Manoj Kumar Chakrabarti sir, Dr. Dhirendra Katti sir, and Dr. Suman Kanunga sir for being here and share their expertise knowledge with us. Thank you so much. Thank you so much all the delegates and participants for joining with us. I understand this is the lunch time, so I will not take much time. Thank you so much everyone. Thank you. Thank you.
Honorable dignitaries, distinguished speakers, dear participants, research scholars, and my dear friends, a very pleasant good afternoon to one and all present here. I, Dr. Seema Rawat, on behalf of organizing committee, feel privileged to welcome you all to this 108 Indian Science Congress Section Committee meeting, Chemical Sciences, Challenges Ahead. We are very blessed and honored to have Professor R. N. Yadav, sir, as a chairperson for the today's session. I request you, sir, to please occupy the chair. Thank you, sir. Respected Yadav sir is a current Vice Chancellor of Purnia University, Bihar. Sir is a well-known scientist in the field of chemistry of natural products and medicinal chemistry. He has 38 years of teaching experience. He guided 39 students for the award of PhD and 4 are currently working under him. He has 28 years administrative experience. He is a recipient of 6 prestigious awards with the Professor K. A. Thakkar Award for Best Published Research Paper. He has many research papers in reputed journal and international journals. We are very blessed and honored to have you, sir. Now I request Professor Vijay Tangde, sir, to welcome Professor R. N. Yadav, sir, with a floral bouquet. Thank you, sir. Now I request you to, sir, please chair the session and start the proceeding.
Thank you for inviting me to chair this session. I invite Dr. Rachna Sadana, Professor of Biology and Biochemistry, Natural Science Department, University of Houston, downtown Houston. She will deliver lecture on the topic. Topic is not mentioned here. I just invite you to deliver the lecture. May I just introduce you? She is PhD in Biochemistry, Kurukshetra University, Kurukshetra. MS Biochemistry, Kurukshetra University, Kurukshetra. Chair Department of Natural Sciences at University of Houston, downtown Houston. Professor of Biology and Biochemistry at University of Houston. Associate Professor of Biology and Biochemistry at University of Houston, downtown. Postdoctoral Fellow at University of Texas Health Science Center, Houston. Postdoctoral Fellow at University of Houston Center Campus. She has done research program Cancer Cell Biology, Discovery of Novel Compounds with Anti-Cell Proliferation Properties and Descripting Signaling Mechanism in Breast Cancer Cells. She has published total papers 24 in peer-reviewed journals. She has grant funded during last 5 years. In 2020, she is member of Advisory Board of Indian Society for Chemists and Biologists International Conference, member of American Association for the Advancement of Science, member of Indian Society of Chemists and Biologists. In this short introduction, I invite Dr. Rachna Sudana to deliver her lecture.
Good afternoon, everyone. It's my privilege to be here today and deliver a lecture. So first of all, thank you ISCA organizers for inviting me. Actually, I consider myself a very confident public speaker, but today my legs are shaking. Here is the reason. Dr. S.P. Singh is sitting here, who I did my PhD from Kurukshetra University. Even though he is not my direct PhD guide, but I have always seen him as my mentor. One of the wisest men I have met in my life. Always has words of wisdom for the most difficult situation. So it's my privilege delivering some science, my contributions to science in front of him. So I'm really honored today, sir. Thank you for being here. And also some of my collaborators and my first PhD students with my guide, Dr. Hari Singh, Dr. Neera Raghav is here. So if I'm shaky today, it's not that I'm not a good speaker. It's they're the reason. So today's title is like a tongue twister for me because I am not a chemist. So if you will read this aryleidine, hydrazenyl thiazole analogs, that's not the part I work on. My work starts when the synthesis is completed by my collaborators. So I'm a biologist. So I'll share some biological testing results with you, which I collaborate with Dr. Ranjana Agarwal, who is not here today, but she's the one who invited me to this conference. So there are a couple of research projects I focus on in my lab. One is anti-cancer drug discovery, at a very basic level. And another one is phage discovery, which is phages are viruses that kill bacteria. So if a bacteria is antibiotic resistant, so phage is the way to go. So I'll share some of that with you all too. This is just basic science. So for students, how to develop chemotherapeutic drugs, what are the targets? So on the left hand side, if you will see right here, it's the signaling pathway, like a ligand binds. Yesterday Dr. Rawat shared NER1 receptor. So there are receptors for cell proliferation. If they are activated, there will be multiple proteins that will be activated, and the final physiological response of the cell will be cell division, right? So cancer is irregulated cell division. So if you have to control that, you have to develop a drug that targets one of the proteins that plays any role in cellular division or cell proliferation pathway. So that's what you are looking at, starting from the receptor, multiple kinases, then transcription factors that initiate cell division. So that's what you will be looking at. So here are some examples of the drugs, so you understand what we were just talking about. You look at that, there is Iressa, that inhibits the receptor. There is avastatin that inhibits angiogenesis, means controls or blocks blood supply to cancer cells. So this picture represents various molecular targets for chemotherapy. So the question is, we have so many chemotherapy drugs in the market. Why are we still beating this dead horse, right? So there are too many diseases, emerging diseases. Why are we not looking at that? Why do we still need more drugs? So this, establishes the importance of the work. Early diagnosis of cancer is difficult. If you know anyone in your family, the symptoms are so common, flu-like symptoms, like you can say cold, fever. They're so common. If you Google cancer symptoms, Google will tell you, you have this and this, you have cancer for everything, right? So diagnosis is so difficult. The second reason is it's not 100% curable. There are only few cancers for which you can extend your lifespan by 10 to 15 years or 20 years, right? But nothing is 100% curable. So whatever you look at, like death rates, it's only survival rate extended by 5 years. So here is some data. You will appreciate that. The blue line is cancer's deaths rising until 1990. Then it's not declining, but the slope has diminished, right? Slope has slowed down. If there were no chemotherapeutic drugs, the death rates will be the red line you're looking at. So with these discoveries, cancer death rates have been reduced, but not eliminated. So we still are in search for new drugs. So these two graphs you're looking at is from American Cancer Society. They calculate this data every year, and you can find those statistics there. So we were just talking about what is the diminished rate from 1990 to 2018, 2019. The reduction in death rates per 100,000 people is only 20%, which is not significant, even though billions of dollars have been spent on this search. And additionally, almost 2 million new cancer people will be diagnosed with cancer only in United States, and approximately 600,000 deaths are estimated. And every 1 in 2 men and every 1 in 3 women will be diagnosed with cancer. That's the estimation. So we definitely need new drugs. You saw a similar graph from Dr. Rawat yesterday. Like, drug discovery is a long process. It takes 15 to 18 years. Starting with 20,000 molecules, you get only one that makes it to the market, and it's hundreds of millions of dollars. So the question is, what do I do in my lab? I work at base level, at cellular level, screening of chemical compounds for their cytotoxic effects. So that's the project we do in my lab. So where chemists stop their work, that's where I start my work. So this is what we do. I'll skip this. Today what I'm going to talk about is, because we haven't published this work, so I am just showing you the core compound, not the functional groups or the analogs, what are showing us good results. So this is the core compound, arylidine hydrazenyl thiazole analog, which has been functionalized in multiple analogs by Dr. Agarwal's lab, and this is what we have tested. So they sent us 20 different compounds. So I have made it little educational because there are so many students here. So for senior scientists, I apologize if it is redundant, right? So students can follow this talk. So for cytotoxicity, what we do is we add a yellow compound that we can see here on the cells. And if cells are healthy, it means the mitochondria in the cell is functioning. It will be converted to purple color that you can measure using a spectrophotometer. But if you add a compound that kills cell, then yellow will remain yellow and will not be reduced to purple, right? So this is how this works. So you are looking at absorbance level indirectly telling you cell proliferation, percentage of cell proliferation. So the compounds we tested, you will see we have used a positive control, doxorubicin, on the most right side. So that is our control. It means the assay is working. Out of 20 compounds, 371, 376 and 379. All of you know these are codes, and PS is no special thing here. It's the person who has synthesized. I'm not sure if he's here, Prince Sani from Dr. Agarwal's lab. So that's the code here, right? It's no secret code. So 3 compounds showed significant cytotoxicity or inhibition of cell proliferation. So this is an example for BT474 cells. I will not show you all 5 cell lines. I'll just show you a table which may be hard to read, but you can see 2 breast cancer cell lines, 1 lung cancer cell line, 1 leukemia cell line, and 1 pancreatic cancer cell line. When we did the screening, these 3 compounds show significant reduction in cell proliferation across all 5 cell lines. So those are 3 compounds we'll be investigating further. Once we screen and identify, you can say, compounds that work, we look at how do they cause cell death. Before we go there, I'll show you some morphological data, microscopy data that shows how cells are not doing well in presence of these compounds. In the first top panel, these are MCF7 breast cancer cells, very flat or large and attached. But if you add a drug, one of these drugs, 371, 376 and 379, you can see cells which are rounded and not attached. Very similar to a doxorubicin, which is an anti-cancer drug, which is a known anti-cancer drug, right? Just for the control, we used a compound just to show it's not any chemical you add and you see a similar result. You can see 373, which does not show cytotoxicity. Cells are doing pretty well. They are attached and flat and large. So this is some microscopy data that complements the data I just showed you from cellular cytotoxicity. Next, we try to see if the cell death that's happening is apoptotic or necrotic. So apoptotic death is a programmed cell death. It's clean cell death, so there is no inflammation. But necrosis is cell is broken, cell component is released and causes inflammation. Nobody would want to take a drug if it causes cell death by necrosis, because you don't want to have inflammation if you're taking a drug. So any drug that you take must cause cell death, apoptotic cell death, right? So there are cellular markers. One of the marker is caspase enzyme activation. So here what you're looking at is increase in fluorescence, means the enzyme is activated, right? So all 3 compounds caused caspase 3 and 7 activation, which you can see here, and the camptothecin in an anti-cancer drug that is known to cause apoptosis was used as a positive control. So these days, you send these in vitro data, reviewers will send it back and say, where is cell imaging, where is your cellular data? So what we did with these compounds is we looked at mitochondrial function. All of you must know, mitochondria is the powerhouse of the cell. If that's not functioning, a person is like dead, right? So you're looking at mitochondrial functionality here. If mitochondria is intact, the dye you add gives you red fluorescence. So you can look at right here in, does this work? Okay. So if you look at this panel, these are PBS, is just a buffer, has no impact on cellular function. You see the red dye. But if you add camptothecin, which is anti-cancer drug, mitochondrial function, mitochondrial membrane potential is lost, so there is loss of red dye, red fluorescence. So if you look at 371, 376 and 379, all 3 do not have healthy mitochondria, so there is no red fluorescence. But a compound which is not cytotoxic, just as another control 365, you can see there is red fluorescence. So this is another assay that shows us all three compounds cause cellular death through induced in mitochondria. So here is another assay you are looking at, similar to apoptotic function. If you see here, blue are healthy cells and red shows apoptosis. You add a dye that binds to a lipid in the membrane. So usually that lipid is in the bottom layer, inner layer, but if cell is undergoing apoptosis, this flips to the outer layer and the dye can bind. So you can see increase in red fluorescence. It means cells are dying via apoptosis. So these are our latest results from past 6 months. That's what I showed you. So what are we going to do next? The plan is to look at apoptosis and cell cycle analysis by flow cytometry, which we just purchased and established that it works. And I'll show you a sample data, not with these compounds, but the graph looks something like this. You can figure out where in cell cycle the cells will be arrested. We also plan to look at messenger RNA and protein expression levels, which are involved in apoptosis, using RT-PCR and Western blot analysis. So this is the data we are trying to produce. This is like we did it only with positive control just to know if it works. So just I'll explain that to you. This is, you're looking at cell population here. So based upon what's the health of the cell, how much DNA this has, you will find this in a different quadrant. So you can look at this data. We added camptothecin. So these two show cells are undergoing apoptosis. So within next 2 weeks or so, we'll be doing these experiments with our compounds. So that was about cancer cell discovery we do. So I'll make a switch and share with you, because the theme is science and technology for sustainable development, which is great. So I played with words, and I apologize. No, by no means I plan to offend anyone. So the idea I was toying with is how about sustaining science and technology development, because I teach, all of you teach young generation. I have my own kids. Everyone and anyone you talk to wants to be an engineer or a doctor. Right? Nobody wants to go in basic sciences. It's a long journey. As an engineer, you can start your job after 4 years, but if you want to be a professor, be in sciences, it's a long, painful journey, right? And with that, and with this new generation who has a focus of 3 minutes, we used to have lectures of 1 hour and 15 minutes, but the research shows this generation has a focus of 3 minutes. After that, you cannot have their attention, right? So how do we sustain that what you all have contributed to, all the seniors sitting here, how do we sustain that in coming years or in future? Like, how do we engage people in STEM and motivate them? So I'm going to share with you one of the models we have implemented at my university by motivating young generation and engaging them early in research. So this is not our own innovation, but from HHMI, Howard Hughes Medical Institute. They initiated a program. It's called Course-Based Undergraduate Research Experience, CURE. It means engage students in authentic research in their classroom, in their labs, instead of those cookie cutter experiments we did. 1 week you come in and do Lowry's test, another week you come in, do something. Like, how about having them do a long-term project in the lab? So this is one of the examples. This is a phage program. 210 schools are engaged. In cohort 12, we were part of cohort 6. So we have been doing this for past 6 years. They have engaged 10,000 students. So I'll show you what we can do with large scale research in classroom. The project is students collect soil And they can bring it from their backyard or their community. They do some experiments in microbiology and isolate a phage specific to Mycobacterium, not that the one causes tuberculosis, but a garden variety that is very similar to tuberculosis causing Mycobacterium. So this is not a project that they do, but the goal is to find phage that can that can treat tuberculosis. So that's the long-term goal. So they isolate a phage, you know, they purify its DNA, send it for sequences, do electron microscopy, and annotate the genome and submit it in GenBank database, which is a national database. So their name gets into the national database, they name their own genome. So they have some investment in this project. So this is what University of Houston downtown has done. We have isolated approximately 40 phages. We have sequenced them, and my student's name is in that database. So in total, there are 8,000 phages sequenced and annotated, submitted in GenBank and national database. And I'll tell you how it has played a role in treating a patient in Europe who had multi-drug resistance tuberculosis. So I'll show you that paper that was just published. So this is the paper I'm talking about. There was a patient in Europe. So there was no antibiotic was working. They approached Dr. Hatfull from University of Pittsburgh, who initiated this project. 8,000 samples of phages isolated by students were tested against that strain that patient had. 3 out of 8,000 phages were effective. They prepared a cocktail of that phage and then transported to Europe, and the patient was treated. So you can see the results here, how the improvement was shown. So the impact of this research done by undergraduates is significant. So I just wanted to share with you, and I can tell you several of my students who took this lab, they all came in with the mindset they wanted to be doctors, and half of them now want to go in graduate school. So this is the impact of such projects engaging students in research early on. So these are papers, the bottom 3, and there are 8 of them from my institution with my undergraduate students as authors on it. So the last, you know, how can I leave this behind? Women empowerment, because this is the theme, right? It's a very sensitive topic actually for me, and I just want to give a very short message to young females in this crowd. I can share a little bit about my journey with you all. You know, as a woman, people will tell you, hey, you are married now, you don't have to do anything, now you have kids, you won't be able to do PhD, just forget it, you know, take care, go do teaching in school. That's what I was told in my first year as PhD. Like, because I got married, I had the baby, and I was told, you cannot do it, just go and leave, right? But I can tell you, if you have a good support structure, and I can give some examples here who are sitting here, you know, if you have a good support structure, do not give up on your dreams, right? So all this women empowerment talk can go on, but you will have to walk the walk. Just find a mentor for yourself who will support you. Find a PhD guide who will give you flexibility, even if you get married, even if you have a baby, who will give you flexibility, not lower the bar, but work with you so you can get through it and live your dreams. That will be a real woman empowerment. Anyone who gives up on you, don't believe, right? Believe in yourself, don't give up on yourself. That will be my message for women empowerment. So my journey, just in 30 seconds, I did PhD in 2001. Went as a postdoctoral fellow to United States. After 7 years of postdoc, I landed on an assistant professor job at a teaching institution. Where I am, it's not an R01 research school, it's majorly teaching. 25% of my effort goes into research, but I have been able to publish with my undergraduates. we do not have PhD students. With my undergraduates, several papers on cancer cell research as well as phage discovery. And as of now, I'm working as a HOD of our department, which has 40 full-time faculty and 40 part-time faculty and 1,000 students. So if you don't give up on yourself, you will live your dream. Thank you. I thank you with that. Any questions, I'll be happy to entertain.
Any question? No question?
I am a pure chemist, so I am a novice to biology, but one silly question. Can any indication of necrosis come in simple hematology, for example, just like getting MCV in hematology, if the volume is down, does it indicate that necrosis is down the way?
So, there is a very delicate balance between apoptosis and necrosis. Even with the drugs like camptothecin and doxorubicin, if you treat at a high concentration, if you treat for a long period of time, you will see some necrosis. So it's not white and black. It's not black and white. So it's a very gray area. You have to find the right dose and the right time. Otherwise, you will see so it's early apoptosis, late apoptosis, and necrosis. So you can always see some ratio of necrosis when you do these results.
Any more question? Thank you, Professor Sadana, for delivering such a nice lecture on the chemotherapy drugs, and she synthesized more than 25 anti-cancer drugs and explained about the study of the so many synthesized anti-cancer drugs. Thank you very much. I would like to know one thing, Professor Sadana. You are in University of Houston, down nearby Newark, Houston, Albany. Houston River is there.
Houston is in south.
Oh, Houston River is not there. You heard the name of Houston River? एक ह्यूस्टन रिवर मैं बता रहा हूँ, एक बार पानी की जहाज जो है उस पर इतनी बर्फ जमी थी कि ह्यूस्टन नदी में जहाज को लैंड कर दिया गया था और कोई की डेथ नहीं हुई थी। इसलिए ह्यूस्टन रिवर है, इसलिए मैंने पूछा। एल्बनी के पास है वो, न्यूयॉर्क से 1.5 घंटे की फ्लाइट है। एल्बनी के नियर पास में है वो, साराटोगा के पास है। अच्छा, हुडसन रिवर। हाँ हडसन रिवर। जी जी जी, हडसन रिवर। नेक्स्ट, I would like to invite Atul Narayan Vaidya.
He is not present.
He is not here.
Yeah, perhaps he is there.
He is not present. Atul Narayan Vaidya is not present. So,
Sir, 1 minute.
give her memento.
Sir, just a minute. I am explaining. Now I request Professor Yadav sir to please give a memento to Dr. Rachna Sadana madam as a token of love, respect and gratitude. सामने आ जाइए बोलते हैं।
Chairperson should leave the chair.
Thank you, sir. Now I request Dr. Vijay Tangde sir to propose the formal vote of thanks.
It is indeed my privilege and honor to propose the formal vote of thanks and Thank you, organizers, for giving me this opportunity to stand before the learned gathering on this platform. I thank from bottom of my heart the speaker of this session, Professor Rachna Sadna, madam, for delivering such a wonderful talk, and honorable chairman of the session, Professor R.N. Yadav, sir. Thank you, friends.
Good afternoon, everyone. My name is Sneha and I'm host of this session. I request Dr. Ranjit Verma sir to please occupy seat and dais. Verma is a grand student of Acharya Ray, founder of Chemistry in India and co-founder of ISC. Dr. Ranjit Verma is ISC General Secretary elected. He has 45 years of experience in teaching and 10 years of experience in administration. He is also the former Pro-VC of Patna University. He is currently working as Professor for Inorganic and Analytical Chemistry in Magad University, Bodh Gaya. Now I request Professor M.R. Lanjavar ma'am, Department of Chemistry, IITM Nagpur University, Nagpur, to welcome Dr. Ranjit Verma with a token of love. Thank you so much, ma'am. Now I request Dr. Ranjit Verma to kindly chair the session.
Thank you for the nice words of introduction. I have superannuated from the department. Anyway, we have three speakers, invited speakers in this session. The first is Dr. Ramanuj Narayan. I think he is here. And the second is Professor Vinod Kumar Tiwari. He is also, you are here. And the third is A.N. Garg. So the session is going to be very exciting. The first two lectures all are based on click, something which clicks. Chemistry does always click. Wherever you go, you can apply chemistry everywhere, because it is the science of making and breaking a bond. You can apply wherever there is matter, material, anything you synthesize, whether organic chemist or inorganic chemist, you have to do some sort of, so it has some applications everywhere, in science, in arts, in humanities. Just one example I will give. One of my Hindi friends, he met me, one history friend, Professor Verma, I can go to chemistry department and teach history of chemistry, but you can't go to history department. I tell, I accept the challenge. I will go to the department of history and I will teach chemistry of history. Why Iron Age was before Iron Age, because although it is abundant, why Bronze Age came. So this is a Lingham diagram and other things. So explanations will be here. Similarly, Hindi friend, but you can't go to Hindi department. I told you how many rasas are there, 8 या 9 होते हैं. We will be talking about the excretion, the secretion, the chemicals which are found in your brain and leading to that. Anyway, so we have two lectures where the two speakers will be talking about click chemistry because of the Nobel Prize this year. Click chemistry is around the corner, and one journalist told, chemistry is science of click. Chemistry clicks everywhere, but click chemistry is something different, which Vinod Kumar Tiwari will be talking. And prior to that, we have Ramanuj Narayan. He is Senior Principal Scientist and Chair of Polymers and Functional Materials Department in IICT, one of the foremost and one of the institutions we are proud of in the country. He is from Hyderabad. So before wasting much time, I invite Dr. Ramanuj Narayan to speak, and the time allotted is 20 minutes.
Respected Chair, Professor Verma, I can correct it. Before that, he was the Vice Chancellor of Munger University also. And I happened to give one lecture in his university as well. and my all respected seniors, professors who are present in this audience, and my dear colleagues and dear students of this great university. At the outset, I thank the IC organizing committee for giving me the opportunity to talk technology in the audience of chemistry. So it will be a little bit difficult, but I will try to justify it through that how molecular architecture change. You can do whatever you want, whatever you will. So without taking much of the time, welcome to the world of color, paints and coatings. And this is Burma sir earlier age time that whatever he told prehistoric black and white. But what we do as a chemist, that we can do color. We can add color to the system. And once coming to seminar, that this is a sustainability and women empowerment. And what, because women are the source of inspiration, plus you can have lot of innovation by seeing the dressing, by seeing the coloring, and prehistoric time from the cave timing, that even you go to Ajanta Ellora today, you will see how that color is still existing. So what is the correlation for this purpose? And you can understand that in sari, or you go to nail polish, or you go to lipstick, there are three, every place polymer is the base. But if your coating can tolerate some toxicity, but if you are making a polymer like lipstick, that what it is, so that is the sustainability. How you are going to make a green polymer, how you are going to use the biorenewable resources, that is the challenge a polymer or a coating technologist will do. So as a salesman, we have to see that in sustainability where our paint industry is going. Earlier there was only two paints, water-based emulsions or some solvent-borne paint. But today if we'll see that it is coming to the powder coating, it is a solvent-less coating, and once again a great salute to all the chemists who are sitting here, that whatever chemistry you do, that sir was talking about click chemistry and other chemistry that which can be scalable and which can be used, what chemistry you do 20 years back, that we follow at the current in the technological development. So I will try to show you 3 or 4 cases that how your chemistry, very simple chemistry of organic chemistry, has been applied to develop the technology. And then physical chemistry, we follow organic chemistry, we follow physical chemistry, we follow materials chemistry. And today you can remember that what is there in a paint can? It is a 4 materials. One is polymer, that is the heart of the coating formulation. Pigments or filler, that will give you mechanical strength or color. Third is the solvent, and fourth is the additive. But today, due to chemist, can that 4 component material can become one? That is the challenge. Earlier, polymer molecular weight was very, very high. You require more solvent to get the application viscosity. But today, in television, you will see the ad, cross-linking. Cross-linking was done paint in the beginning also, but now today challenge before the chemist, how to make a low molecular weight polymer, means oligomer, and how you will get cross-link. The moment you will reduce the molecular weight, you will require less solvent, and that is the challenge, and that plays chemist, that how to reduce the hydrogen bonding by 3-4 cases I will try to show. And earlier, only for decorative or protective, that was the 2 function. But the moment click chemistry came, the moment nanotechnology came, then now coating has become a smart and intelligent by applying simple scalable chemistry, because in coating you are not going to invest that much how you are going to invest on medicine and those type of system. That's why a coating technologist will always have limitation in applying that in the existing process, how you are going to employ that. And once you are thinking to add intelligence, how to add intelligence and smartness in the existing material. So only you have to change the combination, you have to change the functionality, and it is the chemistry where interface plays a very important role, and green meets nano. That we have to make a green polymer, we have to correct the interface, and we have to modify the polymer in such a manner that you don't require additive. So that is this system, and you can see the particle size reduction, nanotechnology, how it helps. If you see pre-90s paint, you used to stir well before use. Then when submicron particle has come, shake well before use, and when we are applying the nanotechnology, ready to use. So that is the difference of the interface, that if you are able to modify. Why I am making this background is because most of you are not in the coating, because it was known as a formerly art, but it is a science. It is a chemistry, and chemistry and physics play a very important. Only 10th class chemistry. If you want to add intelligence to the coating, you have to remember acid-base titration. You have to remember the complexation reaction. You have to remember the electrochemical reactions. And more than 10th or 12th class, it is not required that chemistry is required for adding intelligence or a smartness to the coating. Then what we do at IICT? Molecular engineering and modification. Take simple materials first, and then try to integrate either through click chemistry or either through some good chemistry which is scalable, and how to combine them and how to add nanomaterials into that system. As a case one, if you take a simple polyester chemistry, but if you are making organic chemistry polyester, very simple. But if you are making a coating polyester, you have to use 4 components. You have to use adipic acid, you have to use isothalic acid, you have to use TMP for cross-linking. And once it is become a 4 or 5 component, characterization becomes difficult, and due to associative hydrogen bonding, you will get more viscosity. Then we have gone through the chemistry that how to reduce that viscosity. In the same molecules, what we did, that we have varied the diol. Left side you can see the neopentyl glycol, then cyclohexane dimethanol, 1,3-propanediol. Viscosity reduction was very, very uniform. But then we have scanned the organic chemistry. If you want to compromise the, if you will add beta ketoester group to your hydroxyl group, you will not lose the cross-linking, and you will reduce the viscosity, and that will also help you in getting the adhesion. And almost 12 publications we have done onto this area, and this is being applied to the industry in polyurethane coating. So simple, because as an organic chemist, you will treat diketene, alpha-pinene or meldrum acid, but as a coating chemist or polymer chemist, I cannot afford to do that. But simple, once you are making polyester at 240, you bring it down temperature at 140, a simple trans-acetylation will reduce the viscosity, or it will attach to the system. And we have started with a 60% solid polyester that has gone to 90%. So that is the miracle of chemistry. So this I wanted to show. In right side, if you see a graph, that is the measure of cross-linking density. With a similar cross-link density, with a less solvent, we were able to develop a sustainable coating. And in particular for polyurethane, if you will take, in polyurethane within 15 minutes you have to apply, but if you are modified through beta ketoester chemistry, you can apply till 45 minutes. So that is the reactivity has been slowed down. Similarly, a structural modification, can we add water? Right now I was trying for solvent. Same polyester chemistry, we have reacted with the isocyanate and then modified with the carboxylic group. And this was the very first report where reactive polyurethane dispersion, that it is cross-linkable. Either you can cross-link it hexamethoxymelamine and in a baked type of system. So it will give a water-based protective coating, not water-based decorative coating. A small structure tweaking will help you, because time is less, that's why I'm going on fast. Later on we can discuss. But now, challenge with sustainability, what will come? Don't use neopentyl glycol, don't use this system. Can we use castor oil? Can we use soybean oil? Can we use that with a small amount of modification? And you can see we were able to develop a castor oil based system with a dual function. It will cure this with a moisture, with a polyurethane reaction, and then you can also moisture reaction with a sol gel chemistry. So this was a hybrid coating developed with a modification of simple castor oil. We have not stopped at this place. Can we make some hydroxylation reactions, that whatever you do, epoxidation and hydroxylation reaction, can we make 100% solid coating using castor oil and soybean oil? And we have been quite able to successful. And today, a thermal insulation coating with without solvent, we have gone to the scale-up level, and this is the level of thermal insulation coating at 50 liters we have developed in lab. So if you will apply this coating below your surface of the roof, you can get a temperature difference of around 8.4 to 8.9 at the peak summer, 12 to 2 p.m. But air cooling, because air cooling is not from, it will hit from the wall also, air cooling is 1 to 2 degree. So that is quite remarkable, because 1 degree cooling will save you 10% of air conditioning cost. So it's a small chemistry that how you can do. And then same castor oil, can we make it hydrophobic? Already castor chain is having some hydrophobicity, and then how to use the sol gel chemistry. That chemist has adopted the physicist sol gel chemistry for making the innovation and for making the nanotechnology, and that place with a different contact angle, we have able to improve almost castor oil. Here report is around 113, but we have reached to 135 degree with a simple sol gel modification of the castor polyol. Then this place, because today sir has introduced that click chemistry, we are experimenting hyper branch polymer. Right now our bread and butter is complete hyper branch, and you tell whatever chemistry it can be employed. One example I will show you, green material glycerol we have taken. With glycerol, if you go for a sol gel reaction, you can get a hybrid coating, and in right side, very important, what is applied to your optical lenses. For that, how much we pay, because we have given this to ArcelorMittal, that Arcelor company of the glass, Singapore company, hybrid diol combination, and that will displace refractive index of the glass, hydrophobicity of the glass, and adhesion were almost matching, and this is in the commercial use. With a simple chemistry, simple thinking, we can do the technology. Then come to click chemistry, alkyne azide click chemistry. We have also started in around 2012-13, and alkyne azide click chemistry, how it can give you. We have thought for antimicrobial. Already nitrogen group is there due to urethane. If we will put more nitrogen, our intention was that, but you see how result will be coming. So antimicrobial and corrosion protection, these two, once we have done the simple chlorination step, then agitation, and then put the urethane reaction, we have got a very good antimicrobial coating and with a very high corrosion resistance. But if we have changed the raw material, that is the molecular structure difference. You can see tomorrow Ranjit sir may not require that somebody has put a scratch in his car. He will be happy that you put in outside sun for 10 minutes, it will automatically heal. That is the power of click chemistry. It was unintentional. Once we were making the film, some scratch has come, then that place, once we have put only hair dryer for 30 minutes, it was automatically healed. Then it has again increased our that how many times it goes, around 70 times this click reaction will be effective. Even we have separated it out, right side you can see, red base you can see that you can add like a gum. You press it, hit it, it will join. So that is the another example. Then like that we wanted to modify this carbon nanotube, and once we have click modified it, it was another finding. That was while measurement, it was unintentional. We do UTM, that universal testing machine measurement. So elongation was very high, but some heat you will put, it will come back to its original shape. So you can understand that a aeroplane which got from room temperature to minus 40, minus 60. So in those type of places, this type of coating will be of high use. So that was the another application. And then if we will give a transparent coating using the same zinc oxide nanoparticle be modified with the click chemistry, and the result is a transparent coating, and you put some light, you will get a fluorescent light. So this is the concept what we are exploring, that morning your color car will be different, afternoon your color car will be different in this. So this is that is the fundamental basis in UV blue. When the same light will come, it will become vivid, we have to follow. That how to do that. So these are the concept where click chemistry help you, that how chemistry can help in structural modification. Same antimicrobial coating we have applied for during corona time. We have developed one air purifying device, 8 hours you can wear. That place in that filter, we have put this antimicrobial coating with a zinc oxide based system, and this machine is just like a lab safety guard. So it was a Nimitli project, and we have developed it. So with a power bank you charge, fan will be there. So you can apply on this, and 8 hours you can wear. This is for mining, this is for health barrier, because time was not there, otherwise I should have shown the video. It was tested at Chitra Medical in Bangalore, that even dentist has tested it. So this was our work from the coating and the 3D printing side in IICT for the corona. Other than the corona lecture will be coming in the second session. And these are the two messages I want to give, that this hyper branch polymer and salt jelly will combine. You will become a smart and intelligent materials and coating developer. There is a n number of possibility, and we have to always follow the nature in design of the sustainable material. And I invite all of you that we have got a Center for Excellence in Polymer Coating. We have all the facility that whoever want to explore their experience in coating, you are most welcome to come to CSIR IICT to explore your coating research capability or development, that whatever you want, we have all the facilities, and all the work will be possible due to the support of our director, head of the department, all the students, and most important, the funding agency. We have got funding all across, including the company and including the funding agency. Thank you all for your patience listening. Thank you.
Thank you very much, Dr. Ramanujan Narayan, for the wonderful lecture, wonderful, exciting lecture. If you have noticed, several clicks are there, but beyond click chemistry, there are other aspects also. Any question, if it is coming to your mind, you can put. I think one or two quick questions we can take up. Just one silly question coming to my mind, because I am a really silly person. We are facing problem of burnt used oils, edible oils. So can we, Professor G.D. Yadav was also talking very much about how can we recycle and convert into acid the waste. We should not call it waste. So can we, instead of the castor oil, can we try burnt edible oils also? I think we can do it.
Thank you, sir, because already we tried it, sir, and it is quite possible, because दो time में आप पूरी छानेंगे, it becomes itself polymerization starts. That's why one time you fry the puri, it is good. Second time you will not able to digest. So after one polymerization you have to give to us, and it is already done into the polymer science. The major problem is there for collection, sir. That technology of polymerization, technology of their use in coating is there with us, but the problem in collection, because this work is being done at Australia also, that it will go to RMIT University, and in our place also, even some catalytic route are there. So we have worked on that, but the major problem is that how to collect, because people will be transferred from.
But the technology is there. But the technology is there. Yes. The science is there.
Yes, science is there. Even lot of things can be done. But 5-star hotel will go to Road Star Hotel. Road Star will go to Jhopri Star. So that is a problem. We were not able to get the aisle. As a researcher, we do, but the problem of the supply chain.
Actually, earlier the Indian practice, particularly in North India, we were in the habit of using edible oil only for half frying. Now we are going for deep frying. So it is only the thermo-oxidative degradation and cyclization, other things are taking place. So how to, so we have successfully tried turmeric and other anything. So that is beyond the scope of this lecture. Thank you very much. Now on behalf of the organizers, we are glad to present to you a memento. I think we can have a snap. Thank you, Dr. Narayan. And I am really thankful. I remember we had, because I was the founder vice chancellor at Munger, so we are in the process of establishing the university, and meanwhile the COVID and other things came, and during this term we organized national level seminars, very wonderfully arranged, and he was one of the speakers, I remember. Thank you very much again. Next speaker is again an organic chemist from Varanasi, winners of many awards, Professor Vinod Kumar Tiwari. He will be beginning with click chemistry and bi-orthogonal chemistry and the topics that were in the news. And the topic that he will be, click chemistry as Nobel Prize reaction for the year 2022, the growing impact in glycoscience. So he is a recognized, accomplished carbohydrate chemist, I should say. And Professor Vinod Kumar Tiwari, he was awarded prizes by Science Congress, in Indian Chemical Society, in Council of Chemists, incidentally, the three organizations that I am associated with. So thank you very much for coming, and I would request you to start your lecture.
Thank you very much, sir, for such a kind introduction. Today I am going to talk about the click chemistry, a Nobel Prize reaction, and I will focus the application of click chemistry in the glycoscience, the area which I covered since last many years. I am working on the carbohydrate chemistry, making molecules, sugar-based molecules for various purposes, ranging from the diabetic, anti-cancer, anti-tubercular agents, some part of the catalysis, some part of the sensing also. But the area here, the click chemistry and carbohydrate chemistry by CSIR, funded by CSIR and DST SERB, two projects I will cover today in my talk. So you know the carbohydrates are very important molecules, region are following. For others this is simple rose, but for me this is the anthocyanidin glycosylated, and the color of this red rose is because of this sugar. The second example, you see the cinegreen, which underwent the Hoffman type degradation or Hoffman rearrangement. Basically Hoffman, Lassen, Curtius, Schmidt, all the reactions were inspired by this reaction. Glycosylated thioglycoside underwent the hydrolysis, then carbon to nitrogen migration of this allyl isothiocyanate, giving to the formation of allyl isothiocyanate, bitter taste. The other example you see here, the broccoli, green vegetable. People always suggest you, please take green vegetable in your diet. Reason is the following, because they are rich source of the thioglycoside, which underwent the similar type of the carbon to nitrogen migration. It lead to the formation of sulforaphane, one of the anti-cancer drug. So whenever you are eating the broccoli or green vegetable, you are eating the molecules. The major was the thioglycosides. A slide will be here, you can take back, no problem. And please cover the slide. The slides are more beautiful than me. Yeah. So another example, you see the arabinose sugar, O-glycoside. This compound is isolated exactly 27 years before, and this compound is claimed because this attracts the male gametes at the concentration 10 power minus 12 molar, very low concentration. This is claimed to be responsible for falling in love, and this is dangerous compound because once you are in love, you are no useful at all. Another example, you see this is the simple compound, looks very simple but very useful compound, very sweet compound, known as the vanillin ice cream you enjoyed in the conference. And the vanilla ice cream, if you not put this compound, stabilizer, this will be melt in minutes. Therefore, the role of sugar is in the vanilla ice cream also. And once only you change the OH from para to meta, the compound is no useful for the kid because this is for the whiskey, right? And I'm still happy that I'm kid. Yeah, thank you. Now the Nobel Prize reaction, you see the surplus, basically what he did, the asymmetric hydroxyl epoxidation, you know, in 2001, he was awarded for this reaction. He is able to have the a symmetric version of the chiral molecules, depends upon what the reagents he used. And this work is awarded with the Nobel in 2001. In the same year, he established the second Nobel. And how you see the click chemistry, just the previous speaker, Professor Ramanuj, explained the click chemistry, azide alkyne cycloaddition reaction. But click means the reaction which is very easy to perform in the lab. There is no side product, the 100% atom economy. And if there is no requirement of any hazardous compound, you can put the reaction in solvent-free synthesis, you can save the environment. The reaction should be highly regioselective, many times the stereoselective. If all the criteria is having in one reaction, that is known as a click reaction. So Professor Tukadoji, a carbohydrate chemist, and Professor Sharpless, Professor Meldon, all together they awarded for the Nobel Prize for this year. And what Professor Meldon did in the click chemistry, you see the azide reaction with the alkyne. He is a person of peptide chemistry, and therefore he used the peptide alkyne. And during the reaction, copper iodide and dipia base he used, there is a regioselective formation of the triazoles. And his paper was published in the JOC on the 2nd of April in 2002. And just before this publication, 7 days back, before this one, so Professor Sharpless submitted his paper to Andrew Kemawante, where he used the copper 2 ions, for example, the copper sulfate in presence of the reducing agent sodium ascorbate in water system, and then it led to the formation of the same compound, same type of the compound. Only these 7 days, he was very happy. 7 days because of this one, and he was awarded together for the Nobel Prize. The third one, you see the click chemistry, who discovered, this is very interesting story. Professor Meldon and Sharpless, they claim for the discovery of the click chemistry, but Professor Hodgson, he was the person who published more than 44, 46 beautiful paper in 1960 era. But before that, Professor Michael was the person who discovered the azide alkyne cycloaddition reaction, and in 1893, about 107 years before the discovery of this reaction. And surprisingly, the Michael was not known for the azide alkyne cycloaddition reaction. He is known for the Michael addition. His paper, you see the Michael addition, Michael donor acceptor in presence of the base. It gives the compound adduct. This paper was published in 1887. But before 4 years, in 1883, the same work was published by Professor Komnenos. It means the Michael addition given wrong credit for the Michael addition. The person behind for this Michael addition is the Professor Komnenos. And surprisingly, the Michael discovered the click reaction who has not given any credit. So it happens in the literature because the people are very, very hungry to give the wrong credit to the wrong person. Yeah. You see, the click reaction is very easy to perform in the lab. Maybe the one reason is what? The triazole itself catalyzes the reactions. Once the reaction starts, autocatalysis. This is claimed. And the second one, how it useful in the literature, in the different branch of the science, because amides, if you see the medicinal chemistry, 65% of the drugs are amides. And here, the triazoles are isoester of the amides. But they are very stable compound, very easy to make in the lab. And here, previous year, if you see the literature for the Nobel Prize, the prize goes to the asymmetric version of the organocatalysis. And the asymmetric version, not the asymmetric version, but organocatalysis is also known for the click reaction. This reaction was discovered in 1902, 120 years before of today. And they used the base. Ramachari and other person, they discovered they used the proline or other bases. DBU he used. And the reaction can be done in the photocatalysis. Here the topological chemistry you can do for the polymer, glycopolymer, and several approaches there applied. Here we have the anomeric position of the sugar. We can have here the means simply the agitation. One part fashion agitation followed by click reaction, you can do perform the click. This is our work where we can do the Michael addition followed by diazotransfer reaction, then followed by the click reaction. All together we can do, but we did perform the reaction 2 steps. The first step, Michael, followed by the agitation, and this reaction, the yield are very good, and selectivity is also very good. You can perform the reaction in triazole forming reaction in the flow chemistry. One of the example is here. Azide alkyne cycloaddition reaction can be done by the intramolecular fashion. Beautifully we can perform the reaction. Since last 2-3 years, you know that we are suffering a lot because of the virus, but we already invited the virus. Yeah. In 2010, when the virus was silent, we are just excited him, the virus, how virus can be glycoconjugated by means of the click chemistry. You see, one example I have shown here, the click chemistry can be useful for the bioorthogonal concept. I will focus this part in the next slide. You see how this reaction, the strain promoted azide alkyne cycloaddition reaction can be considered for the bioorthogonal coupling. Reaction is very widely explored by Professor Tukadoji in 2004 Jack's paper. What she did, I will discuss later. But before that, you see the triazole forming reaction, you need the catalysis, copper catalysis. If you want to have the opposite regioselectivity, you have to use the ruthenium catalysis. But in the living system, you can't do the reaction with the catalyst. We need either the organocatalysis or catalyst free synthesis, and what she did beautifully you see in this next slide. So the second paper, first paper by the Michael, and the second paper was published on this area, sir, by the Professor Wittig. Wittig was Nobel Prize winner. He do not have any time for the other research, but he did perform the reaction here, the cyclooctane. This is highly strained molecule up to the strain free, to strain promoted click reaction. There is no need of any catalysis. You can do the reaction in absence of the copper or ruthenium. It lead to the formation of this triazole. And this work was published in 1961, strain promoted concept, and in 1961. Then the second paper, you see beautiful paper, phosphine reacts with azide. It lead to the azahalide. This compound is great application, but one problem is what? The compound is not stable in the water. And water is the best solvent for the living system. So you can't put this reaction in the biological system, and this method is one limitation. But again, the work was awarded for the Nobel Prize starting the reaction. But the second thing you see, if you put here the COMe group, that can be stable enough. Then this is the first Staudinger ligation, first bioorthogonal concept, where what she did, Professor Tukadoji did publish in the science paper. Then after what she did beautifully, you see this structure, sugar azide is there in the cell, azide can be tagged. Then what she took the Tukadoji from here, Wittig concept. She used here 2-fluorine, then tag with the fluorescent linker, do the reaction without any catalyst. She can put the reaction, and then once we have here, we can monitor in the living system in a very simple way. This is the paper which attracts the Nobel for the Nobel Prize. And this is the concept how we can have here the azide, then tag with the cell, and then we can have here the alkyne. We can react together in absence of the sugar. And the reaction, azide and alkyne, they are not interacting, not interfering in the living system. You can put the reaction in presence of any of the stuff, including the proteins or our enzymes. Basically, the reaction, most important, most complex vessel is the biological systems. Big flask is the simple one. The complicated is the living system, and most complicated reaction vessel is what? The human body. And she put all the reaction in, including in human body. And again, you see why the carbohydrates are very important. If you see the number, molecules, nucleotide, peptides, carbohydrates, the numbers are very high in the carbohydrates, because the carbohydrate has ability to link with the different sugars by alpha or beta linkage. Not only that, you can add the sugar with another sugar via 1,2 linkage, 1,4 linkage, 1,5 linkage, 1,6 linkage, so many possibility. And not only, you can add the sugar with the proteins, glycoproteins, you can add the sugar with the peptides, glycopeptides, so many glycolipids. That's why their importance is very high, their numbers are very high. We can have here the amides start from the aldehydes and the amines in presence of the hypervalent iodine reagent. Professor Tukadoji is the well-known person, and Dr. Dilip is also working on the DIB and hypervalent. I did only one paper. I published one paper in the organic later, and then after I stopped the research in this area. But we have completed many beautiful examples dealing with the sugars, and some of them are very potent one. This compound is 10 times more potent than the ethambutol anti-tubercular drugs. Then you see why this compound is very important one, the Tukadoji concept. This compound is explored in the Nobel Prize. And what I did in this area, you see, in the living system, the cell has lipid bilayer. The last part of the lipid bilayer is what? The sialic acid. Therefore, they are known as the terminal sugar because they occupied at the terminal end of the sugar of the cell. Therefore, they are very important in the recognition, molecular recognition phenomena. And this is the molecule which is attracting the most of the biologists, chemical biology purpose. You see how we can make this compound start from 6 carbon and 3 carbon. We can do the intermediate class experiment in the presence of the aldolase, enzyme-induced aldol condensation. We can have here the 9 carbon sugars in a very good yield. But the mechanism, what I told, this is not very exact one. It took more than 5-year time to establish the mechanism. This work is published in the biochemistry, very fantastic paper in the biological application. And you see, once we put here the first enzyme, then we have here the living group, CMP, sialic acid synthetase. Then we activate by means of the third enzyme, sialyl transferase. We can have here the donor acceptor linkage alpha 2,3 by means of the enzymatic. Beauty is what we can put all the reaction together in one pot fashion. Yield is more than 98%, sometimes 100% quantitative yield. And what is the application of this one? We have here put the reaction the microarrays. We can have here the terminal galactose, backbones is there, fluorescent linker is there, amino group functionality. We can do the one part multi-enzyme synthesis. We can have here the 77 analogs. And out of 77 analogs, 3 were known to bind with the human virus. The another aspect is how we can have here the 2 to 8 linkage, no problem. We can have the fourth enzyme, CST2, that reacts together, it gives the formation of this pentasaccharide. If you want tetrasaccharide, if you want to have the pentasaccharide, no problem at all. You repeat the reaction, and then we have here the pentasaccharide. We published this paper in the JACS 10 years before. Once we have here the alkyne azide, we can react together by enzyme-induced reaction. Then we have here the triazole, then followed by the click. Then again by here the azide alkyne cycloaddition, intramolecular. You know the intramolecular reactions are even more important than the intermolecular, more faster than the intermolecular. We can have here the very nice molecules. Then you see the azide alkyne reacts together in presence of the copper catalyzed reaction. It gives the formation of the triazole, very regioselective triazole forming reaction. They have wide range of the application. We published this work, this review, chemical reviews in 2006, year before. And then you see, when I joined BHU in 2005, this is the first work which I started, azide and alkyne under click reaction. But before that, we published this work. There are 2-3 paper appears in the journal, and from Professor R.C. Lorak, we stopped the research, this one. But again, we have extended the protocol, amino here, first diazotized, then anidation, then we cyclize by means of the chemistry, copper iodide we used here, the base catalyzed reaction. We published this work in tetrahedron later, but after 1 year in 2010, but after 1 year, Professor Ren from China, what he did, he used this compound and same base, same solvent, same thing, everything same, only copper iodide was replaced by the platinum acetate. This work is published in the JACS. Then you see how we can have here the cleavage chemistry. We can react this compound, treat this compound under free radical condition. There is a homolysis. After that, molecular recognition will be removable. Then there the bi-radical can join together. It leads to the formation of benzotriazole. So start from benzotriazole, we can complete the benzotriazole in one part fashion and very high yield. This work is published in the Journal of Organic Chemistry. After 1 year, we modified the protocol, again published the same paper in the same journal. And this is the more beautiful paper. Professor Karade, you read this paper, you complemented it. Yeah. Then you see the acyl benzotriazole kind we have. We activate the acid by a different way. All the work we put together, and here you see most of the work is very highlighted in the organic chemistry portal. I am not going to describe this part today, but there are only 28, 29 of the work benzotriazole ring cleavage chemistry, and out of 28, 14, 15 paper from my lab. You see here the azide, alkyne, here the azide. We can react together by copper iodide base. We can have here the triazole forming reaction, and 2 sugars are linked together. Then we remove these PMB groups by means of the DDQ. Once we have here the OH free, it can attach in the intramolecular fashion. glycosylation. It gives the macrocycle, very beautiful compound, high Rg selectivity and stereoselectivity. We completed the synthesis with several analogs, sugars, basically the glucose sugar we choose. And then you see the sugar alkyne reacts with the epichlorohydrin in presence of the copper catalysis. It leads to the formation of triazole having the OH azido alcohol. This OH can be perparagylated, followed by heating, it gives the marpholin fused triazole. There are 2-3 compounds marketed which contains the marpholin fused triazoles. Then we modified the protocol and there is no need of any catalyst. This work we completed with the 1,5-disubstituted triazoles. We have explored for the application, and this organocatalysis work for the triazole forming reaction we are going to submit soon. Then we have here the sugars basically link with the protein, sugars can link with the steroids, sugar can link with the flavones, isoflavones. Many examples we have completed and paper the biologically relevant molecules there all are. Anoscapine, you know, the anti-cancer drugs, but because of some toxicity, this is not placed in the clinical trials. Then we have here the selectively removes this OMe group from this position to position already intact. Then we have here the perparagylatation followed by click reaction. We have the 14 compounds, and out of 14, 4 compounds we have displayed very good activity against the cancer. 2 we are known for the anti-leishmania, Kalajar. This compound you are already aware that the curcumin, very useful compound, you know, kitchen, but the problem is again the water solubility or bioavailability. What we did, we just perparagylated followed by triazole forming reaction. Sugar is there, all the 4 acetate will be removed, and this compound is 11,000 times more water soluble than the parent compound. This compound displayed very good activity, anti-cancer, anti-biofilm, anti-2 and antibacterial. 3 activity we tested. We contributed 2 papers. One is the Nature Scientific Report and another is antibiotics. Many examples. I'm not going to describe today, but you see here another example is both the triazides were conformed by the single crystal. When we put the reaction in the ethanol, reaction is good. When we put the reaction in methanol, there is a one side product, trans esterification is there, conformed by the single crystal. Diazole transfer reaction, Michael addition, both together we followed by, and then again at the end we completed the triazole forming reaction. Many of the analogs displayed very good sensing properties, and these are all our work. But this work, you see, the compound is very simple and it sends the chiral analytes. And several catalysts we discovered, but one of them is the very good one, because this requires only 10-minute times. We can store this compound in Varanasi having the temperature 48 degrees centigrade in summer. It means the compound can be stored in anywhere world. So, and there is no any requirement of the base, no ligands, nothing else. Only put the reaction in the solvent-free synthesis, the reaction works well. 10-minute time it requires for the regioselective triazole forming reaction. And here you see the azido means triazole glycohybrid triazoles can be used for the ligands having the cyclization from amide to benzoxazole, thiamide to benzothiazole, starting from the benzimidazole and some quinozoline based molecules. We can complete a synthesis beautifully. This work is published in the ACS Communicable Science, followed by this work is recent JOC, where we can have here the alkyne and aryl halides. If you heat the content, there is a Sonogashira coupling. Otherwise, we have here the glacier coupling at the room temperature. Only 1-2 minute time I will take, sir. And this catalyst again useful for the tandem reaction of the quinozoline, very important molecule in the drug discovery development. Recent JOC, we are going to submit this work, sir, within next 10-12 days. I hope that we will be prepared. You see, this is a fantastic molecule, silicomolybdenic acid. That compound is very useful for the acetonide protection. Only 2-minute time it requires for the sugar protection. You can do the reaction with the glycosylation reaction already undergoing in my lab. We can do the benzotriazole ring cleavage chemistry. And when I was in the train, I informed by my student that reaction is going to catalyze the porphyrin synthesis. We can replace the propionic acid, and yield was improved from the 12% to 90% about. So this is the compound which we are on the way to explore in my lab. And you see the another sugar is where the ring oxygen is replaced by nitrogen. This is amino sugar or EJA sugar. This compound is very useful for the alpha glucosidase inhibitors. Many compounds is marketed. One of them is the deoxynitromycin, and one is the galactose derivatives for the Fabry disease. Professor N.G. Ramesh from IIT Delhi is working on this amino sugar chemistry. and Professor Dhawale, Dilip Dhawale, Professor Y.D. Vankar. So we have completed this total synthesis in RSC Advanced in the 2013. 10 years before, and start from here olefinic ester, first Michael addition followed by reduction, then Miss-Nebu cyclization, then we remove this isopropyl followed by removal of the N-benzyl, O-benzyl, then we have the ONH group. It can attach in the anomeric center, and there is a cyclization we can reduce by means of the hydrogen platinum carbon. So this started the chemistry, and now you see the glycodendimer start from this phenolic ester. We first propagylate, then reduction, then chlorination, then we do the click, then agitation, then again click. We can have here the dendrones. This dendrone will be coupled by means of the copper catalysis. We have here the porphyrin core meso position 4 porphyryl group, and we have completed this beautiful molecular architecture. One of the structure is here porphyrin, you see in the core, and 24 sugars at the periphery. This compound is published, work is published in the JOC, but this has wide application for the photodynamic therapy, may be useful for the cancer treatment, but we have explored only the chemistry part, biological part is still missing. Then here the sugars, not sugar, non-sugar, both together. This is the hybrid system. We contributed the synthesis and published the work in recently in 3-4 months back. Then here you see start from the simple core, we can completed the synthesis. There are 18 sugars at the periphery, and core is the benzene core. And this compound displayed very good activity, anti-biofilm and antibacterial activity. Then caligirane system we have explored, and there are the triazole and benzotriazole together, and the compounds were displayed very good activity again for the antibacterial. Here we have the caligirane glycodendimer having the triazole linkage, and this chemistry was further explored for the glycodendimer. One example is here, 27 sugars at the periphery, and this compound is very useful for the sensing. But we completed published the only part of the synthesis in the RSC Advances. This is invited paper in the carbohydrate research just 1 year back. There are 36 sugars at the periphery, and here the DOTA, theta are the molecules. This compound should be useful for the MRI agent, but we explored only the chemistry part, not the biology. Here are the 54 merged sugars at the periphery. This work is not published yet. We have the NMR data, but MALDI data is not supporting. We are struggling for the characterization. Once we characterize, we publish this work. So conclusion is very easy that click reaction can be done. Sir, 1 minute more. So click reaction can be done as alkyne cycloaddition for the glycodendimer synthesis. We can modify the surface. We can have the triazole forming reaction for various purposes, ranging from the asymmetric catalysis, microcyclization, and glycodendimer, drug discovery development. Nanotechnology we can do. We can modify the nucleoside also by means of this one. This is my journey, what I did in last 21 years, starting from the development of the diverse range of the glycohybrids, means biologically relevant sugar-based molecule, 20 years of our journey. This is not only my journey. I'm a single author, but the journey is with my students. And this is the second chemical review which we published just recently. This is 319-page long article. I think the world longest paper published till today. This is invited paper. You see there are only two books. One is the Wiley by the Professor Widjak, and one chapter from my lab. The second book is by Professor S. Chandrasekharan, Indian Institute of Science, Bangalore. One chapter from my lab. There are one review article, means one thematic issue of the chemical reviews, thematic issue, one chapter from my lab. Total 551 page for 13 chapter, 319 page from my chapters. So this is one more that science of synthesis from the Germany. There are several chapters, one chapter from my lab, experimental chapter basically. And this year the click chemistry Nobel Prize reaction goes to Professor Bertozzi, Professor Meldon, and Professor Sharpless. And conclusion is very easy, that azide-alkyne cycloreaction in presence of the copper catalyzed, it gives the regioselective triazole formation. This is a concept delivered by the professors Professor Sharpless and Meldon. This work was published by the Professor Wittig in about the 70 years before, and this work was widely explored by Professor Bertozzi in the living system, biological system, and this is basically the breakthrough for this year Nobel Prize. There are several analogs which have the biological activity, but one example I have shown here, curcumin glycoconjugated, developed from my lab, and the application, this is TOC of our chemical reviews. The notable advantage already discussed today, the bioorthogonal coupling, click to gelation, click to chelation, click to catalysis, click to glycation, and finally the click to Nobel. Sir, I delivered lecture in your university. I already told that this work will be certainly recognized by the Nobel Prize after 10 years. But I was wrong. It was awarded in 1 month, 1 month or 2 months. Yeah. Not 2 months, 1 month. Yeah. So I dedicated this review to the Professor Karl Barry Sharpless. We have exchange of some mails, more than 20 emails we have exchanged. Then we dedicated this chapter to him. He was happily that the chapters was nicely written. I'm thankful to my student, all the PhD student. Because of them, I have 165 paper, and out of 165, 65 is focus on the click chemistry, rest on the sugar chemistry other than the click. And I'm thankful to my alma mater, Banaras Hindu University, CDI Lucknow, University of California, University of Constance, Germany, University of Florida, and 10 major products I have. This is one of our means university logo, you know, ये सर्व विद्या की राजधानी. जब हम सुनते हैं इसको तो खुद लगता है कि something I am. ये सर्व विद्या की राजधानी. This is the book which I edited for the carbohydrates in drug discovery and development for the Elsevier. They are very happy with me. They again invited me to have the duplication. I regret. I don't want to do any duplication. Then I shifted to the synthetic strategy in carbohydrate chemistry. They have accepted. We are on the way to publish this work in next 5 to 6 months. This is the green chemistry book we published. This is one project. I am accepting the invitation from the molecules. If you want to can submit for the publication molecules, and one more, recently I accepted invitation from the synthesis, very highly reputed journal from the Germany, for the thematic issue of the carbohydrate chemistry. Non-carbohydrate paper we are unable to accept, but if you have any paper related to the carbohydrate, please submit me. Yeah, thank you very much.
Thank you very much, Professor Tiwari. One or two quick questions, please, because we have to maintain the time schedule.
This slide will be here.
Yeah.
Yes.
Professor Tiwari, fantastic work.
Thank you, sir.
I was wanting to share. It's interesting. I don't have any questions.
Thank you, sir.
Yeah. Good comment. Any question? One curiosity is coming to my mind, Tiwari ji.
Yes, sir.
And number one, I perceive from your lecture that Bartoji got inspiration from Staudinger.
Yes.
Your work, perhaps. And second thing, that because of the highly selective reactions in click chemistry, snapping just like the seat belt in car, so it is, I think it has immense potentialities in drug delivery.
Yes.
And reducing the quantity of drugs, sustainability, it is a big breakthrough. So I think if we combine nanotube chemistry, chemistry of or nanochemistry with these things, I think we can have wonder. One click I am just intending to share. Our students in, although big stalwart of ferrite chemistry, Professor Gajbee is sitting here, but I think he will agree that barium hexaferrite are so hard and so difficult to synthesize below 2000 degrees Celsius only. We were trying for sol gel, precursor, and we were heating precursor. We are just trying, okay, because of some discussions. I instructed them to heat it for 12 hours. After 6 hours, the boy got okay, because there is some power problem, some repair is going on, so we will have to shut it down. So 6 hours have gone waste. Immediately it came to my mind, why don't you go for heat quenching? Immediately from oven, furnace, he put it in, and we got wonderful barium hexaferrite nanomaterial. So sometimes it clicks. Okay, thank you very much. Thank you very much. And on behalf of the organizers.
Thank you, sir. This slide will be here. You can take copy from the computer. I already given, yeah. Whenever I deliver lecture.
Slides were there at Munger also, I think.
हाँ, मैं जहाँ भी lecture देता हूँ, वहाँ मैं slide छोड़
हमारे यहाँ गए थे,
जी.
Now after these two lectures, we are going to listen to a legendary figure in the field of Masbauer spectroscopy, for which IIT Kanpur had also been in, and Nagpur Institute of Science, and so many institutes are there. Professor A.N. Garg is here, and when he comes, we remember one analytical technique which is missing, which has been missing in the recent sessions of Science Congress, neutron activation analysis, the applications that he was able to make it everywhere. So analytical chemistry, you know the tool, you can apply in any branch of chemistry, not only chemistry, everywhere. So the versatility of analytical chemistry, I think you will listen to his experience. Professor A.N. Garg, he retired from IIT Roorkee, and he started his career at Udaipur, now Mohanlal Sukhadia University, and in 79 he migrated to Nagpur, and after that he went to Roorkee, and in between he had good periods abroad under various schemes. So his contributions are immense in these two, particularly in these two fields. I invite him to share his experience and inspire our young scientists. Professor A.N. Garg, Amarnath Garg. He is former member of the Executive Committee and Council of Science Congress also, and sectional president of the Chemical Sciences Sector.
Mr. Chairman, my mentor friends, at the outset, I am grateful to the organizers, Science Congress, and especially my senior friends, Professor S.P. Singh and H.P. Tiwari, due to whose courtesy I am standing before you today. As it was mentioned, in 2001, I was sectional president when the session was held at IERI campus. And then up to 2004, I used to attend as council member. So this is after a gap of almost 17 years that I'm attending Science Congress. Then I really feel honored to be here in this room where I have lectured to my young friends as a teacher when I joined here in 1979. So it has been a long journey for me, moving from places to places like a Banjara, and for that reason I was not considered as a person who could be eligible to get pension even after serving the country for 34 years, continuously from 71 to 2006, when I finally retired from IIT Roorkee. They say that India is one, but I think India is not one, because I kept changing the states. So here I will be sharing some of my thoughts, which is essentially due to my students over here and then at Roorkee. During my career, I worked in several areas, all using radioisotopes. So far you were having the high dose of organic chemistry, but now I will take you to a different word of radioisotopes. I have used radioisotopes to the different kinds of applications. Friends, now the situation has changed after the sad accident in Delhi University, when the gamma chamber was sold to some scrap merchant. So, and they have put so many restrictions, and now it is very difficult to get any kind of radioisotopes in the university system. Well, the first love of my scientific research was mass spectroscopy. where I worked as a PhD student at IIT Kanpur with Professor Goyal. Here we studied hydrogen bonding in ferro and ferricyanuric acids, identification of covalent bonds. Then I had set up this facility over here in Nagpur University, and then I moved to Roorkee. There also one of my students, she worked on spin crossover studies in diethyl thiocarbonates, and that student is now head of the department at the Punjab University, Chandigarh. Then another major field of mine was neutron activation analysis of major, minor and trace elements. I started working with the lunar samples, and then because lunar samples could not be available all the time, so after coming over here, I started using that facility for the analysis of this environmental studies, the bio systems, nutritional studies, using americium beryllium isotopic neutron source for the determination of major minor constituents in the minerals which are found in this region. Then the radio tracer studies, separation and determination using radioisotopes, radiation chemistry of solid inorganic nitrates systems studied. That is mostly the physical chemistry type of work, because we had the gamma chamber over here. Then lastly, in the last phase of my life, I had a student, as a Bengali student, Ratnadeep Chaudhary. He was very fascinated to organic chemistry. But because I'm as a neutron activation analysis expert, as the chairman has mentioned, but then he dragged me into organic chemistry. See, so some of the medicinal herbs which we are analyzing, so he started what these phytoconstituents. I'll just give you a glimpse that what he worked. Of course, then I retired and we could not carry out this work. During my career, starting from 1965, after which I joined IIT Kanpur, and then after clearing the candidacy examination or the comprehensive examination, I started work in 1967 till 2006. So this is the journey which I had. That is the IIT Kanpur, worked with Professor Goyal, 65 to 70. Then my first appointment was as Roorkee University in 1971, actually. But I stayed there only for 6 months because I was a temporary lecturer. Then I got a permanent position at Udaipur University. So 79, I was here. From there, I moved on leave to University of Kentucky, USA, as a NASA co-investigator. Then with Professor Eman, 74 to 76. Then after coming back, I was again in the Udaipur University, and from there I moved to Nagpur University in 79. Here there was a position of reader in nuclear chemistry. So I came over here and I was told that I have to justify my position as a nuclear chemist. And although there is no reactor over here, but then I had the opportunity to work with Professor Goyal and also at the University of Kentucky with Professor Eman, who had no reactors. So I said, if those people can work at their places without having any reactor, then let me also try. And I tried, and somehow I succeeded. But if I would have been born, say, 30 or 40 years late, and if I would have been a student now, probably it would have been impossible, because somehow so many restrictions have come up. When I was here at Nagpur, then for some time I was there at the University of Tokyo and Institute of Physical and Chemical Research, RIKEN, with Professor Ambe in 1990. There I did some work, and then I got a Japanese patent. When I moved to Roorkee, where I worked from 1996 to 2006, I retired. After retirement, I was principal in a self-finance college, but there, of course, there was no research. But then I moved to IGNOU. They had started a MSc program. They call it as a face-to-face program because basically their university is meant for the distance learning. I spent about an year. Then I moved to MIT University. There it was a nuclear science and technology department. I was not a chemist for 9.5 years. Whatever I taught was the chemistry courses related with nuclear science and technology. That is your waste management and other things, how to create wealth out of that nuclear waste. And from there, I retired in 2020 February. Okay, so it is almost about to be 3 years since I retired from there. So this has been my journey, my friends, various places. During my career, I had various projects. Council of Scientific and Industrial Research, I had 2 projects, and some SRF fellows. University of Grants Commission, I had 2 projects. Then Board of Research in Nuclear Sciences, Department of Atomic Energy, I had continuously about 5 projects all through my life. And through my contacts in DAE, then one friend, Dr. Mani, who had moved to International Atomic Energy Agency, he was there in the Department of Physical and Chemical Research. So he invited me, and then we had 2 CRPs, they call it as coordinated research projects, for which I got about $30,000 when I was working over here in Nagpur University. So with these fundings, I could set up laboratory over here, as well as at Nagpur University, as well as at the IIT Roorkee. Well, let me start with my work on mass wire spectroscopy. This mass wire spectroscopy, although it is named after this great scientist, Nobel laureate in 1961, he was a physicist because this is a phenomena of physicists. This is also called as recoilless nuclear gamma ray resonance. He was a German physicist, Rudolf Mosswar. Somehow by coincidence, my Professor P.S. Goel, was also a physicist from Banaras Hindu University, but then he was in TIFR, and from there he moved to USA, and after coming back, because he had worked there in nuclear chemistry, so he was appointed as a professor over there. He had set up the laboratories over there. So what happened when in the IIT system, see, you do not have choice. Once you are selected by the departmental committee, you are allotted to someone. Similarly, when I got the students, there is a selection committee who selects, and then they are allotted to the respective teachers. Only the broad areas they are asked. Okay? So somehow Professor C.N.R. Rao, who was the chairman at that time, he said that, well, you work with Goel. I said, sir, this is a little bit rare kind of things, and it may be very difficult to get jobs. He said, why do you bother? You see, when Goel worked, there was no IIT Kanpur. What do you think, that India will not develop? See, you work over there. And well, I started working in this phenomena. And just around that time, because one box containing mass wire spectrometer, at that time it was a very simple kind of device, it has come. He asked me to open those boxes, and then we had set up this facility over there. So I was fortunate to have been the first worker in chemistry in this country. And just around that time, Professor V.G. Bhide, who was at NPL, and then later on he became the Vice Chancellor of, I think, the Pune University. Well, here he was not set up. No, I think that was at the Institute of Science in Bombay. Yes, Bombay, yeah. So, and at that time, nothing was known, and especially as a chemist, so I had to interact with many people. So this phenomena called as nuclear gamma ray resonance, it's a very strange kind of phenomena. Just like when the bullet comes out of a gun, you get a recoil back in the backward direction. So in the similar manner, whenever a gamma ray is emitted from a radioactive source, there is a recoil back in the lattice or in the kind of compound, solid compound, where from it is emitted. And this recoil energy is E gamma square upon 2 mc square. And here E gamma, if it is higher, then the recoil energy is high, and if m is small, then it is high. If you want to reduce, because here it is called as recoil less, so if you want to reduce this recoil energy, you have to have this gamma ray energy as very small, and this m, that is the mass of the solid or the compound, to be little bit higher on the side. So this is the kind of ingenuity of this great scientist he thought of, and that is why this phenomena that developed. Now here what happens when this gamma ray energy is emitted over here, now because of this gamma ray, this recoil less, actual energy which is emission with recoil is less. See, so this is the original gamma ray energy, it is bit less. And if you want resonance phenomena to occur, then you have to compensate this energy loss, and you have to have this energy little bit higher. So then only if there is an overlap, there will be resonance phenomena. And unless you have this 2 ER to be compensated from somehow by giving motion to the source or to the absorb or the system, whatever you are studying, you cannot study it. So this is the kind of thing which he thought as a part of PhD thesis. And my young dear friends, he had only 2.5 publications at that time. It was his PhD thesis, 1958, and in 1961 he got the Nobel Prize for that work. Now here, as a chemist, we were fortunate to have this source, cobalt 57, which is unique, having a half-life of about 270 days. So for a PhD student spending 3 or 4 years, this is sufficient to work. Okay? But this was not available in India because this is produced in a cyclotron facility. So it has to be imported. Okay? And this electron capture goes to this one, and ultimately it is this energy 14.4 keV, okay, which is, we can call it as a Mossberg transition. So you see, energy is very, very small, as we had mentioned just now a moment ago. And iron 57 is also not very low but not very high mass. Okay, so that is why the recoil energy is sufficient to be compensated. And here I started this facility in 1967, and just around 63 or 64, some chemical applications or some chemical parameters, they were found, and one of them was isomer shift. Isomers, as many of you are organic chemists, you know, they are the two structures, different structures, but with different energy naturally. So similar to that over here, if you have this source which is in the ground state that emits, so then it gives a small shift. That is why this isomer shift. And this shift is related to some parameters. This is a nuclear parameter and this is a chemical parameter, that is the electron density at the this nucleus in the system. So because of this, there are chemical applications over here. But this has to be measured always with respect to a standard. And standard, most commonly used standard is sodium nitroprusside. Of course, physicists use iron metal or Fe2O3. Another important parameter for the use of chemists is quadrupole splitting over here, whereby if the system is placed in a different chemical environment which is asymmetric, okay, non-symmetric, so then there will be a splitting, and this separation of these two lines, this is called as a quadrupole splitting. And over here, you see, because of this nuclear spin and other things, you can measure, okay, whether the system is symmetric or non-symmetric. That will become clear as we move on. Then the third parameter, which is of more importance to physicists rather than chemists, that is the magnetic. If you put the system in the magnetic field, or if the system is magnetic, then there is a 6-line spectrum over here, and then you can get the effective magnetic field. Professor Gajwe has worked a lot in these kinds of systems. We also worked, but not very much. The very first system, I was looking for a system because my professor was a physicist, and then we were, at that time, once we had set up this facility, we were looking for some compounds, some simple compounds, which we had ordered. In the meantime, I said, let me do something. So potassium ferrocyanide, you know, iron is surrounded by 6 cyanide ligands in a symmetric manner, okay? And iron is 2+, is surrounded by 6 cyanide ligands to form the octahedral structure in a 3d6 system. And because cyanide ligand is a very strong field ligand, okay, so all the electrons, they will be in the lower, that is the T2G6 one. So all the electrons are symmetrically distributed, and that is why a single line is expected. So as a chemist, I just thought, why not to change this potassium? Let me see if I change to lithium or hydrogen or sodium, potassium, rubidium, cesium. Then I found that if I change this to hydrogen, then it is called as a chemical shift. And the kind of spectrum which we got at room temperature for ferrocyanic acid was this little bit of splitting over here. We were really fascinated and compared it with the potassium ferricyanide at room temperature, which was slightly higher. Okay? When we sent this to the Journal of Inorganic Nuclear Chemistry, which was quite famous at that time, then we were advised to carry out some experiments at the low temperature. We didn't have a cryostat, but fortunately our workshop facilities were good, and we had set up this cryostat over there. So we had to do this kind of development well, and then we found that this quadrupole intensity changes, and the quadrupole splitting also remains over there. The question was that why is it so? Because these hydrogen atoms which are outside there, potassium is purely ionic, okay? But hydrogen is bonded to some hydrogen bonding. But how this hydrogen bonding? Then we found some literature reports with the neutron diffraction and some X-ray diffraction. We found evidence, and finally this paper was published. So this academic journey started in the year 1969 with this first publication. Okay. Subsequently, we studied the systems of, you can say, ferricyanic acid, nitroprussic acid, and some other compounds. And when I came up over here, I had 2 CSIR research projects. In the first one, Dr. Parvate worked. He is now retired. And when Dr. Lanjevar was there, he is also retired. So you see, many of my students are also retired. So I'm an old man, but just now due to the courtesy of my senior friends, thought, because you see, 2006, after 2006, I had no experimental data. You see, so I cannot say that we are working. We worked, okay? So I'm just sharing that how difficult times we had and set up the facility over there. At one time, there was one young friend, Roy Johnson. He was actually working for some catalytic converters in Neary, and he wanted to register himself for PhD. I said that if you want to get PhD with me, you have to work according to me. That means you have to share some of the observations to my interest. So he prepared, or rather he was preparing, lanthanum ferrite system. He prepared it by two methods, co-precipitation method and ceramic methods, and as we shall see, that ceramic method works out to be better. And by the solid state reaction of lanthanum oxide and ferric oxide, and a 6-line spectrum was observed with isomer shift and this magnetic field. Now, when this system has worked, as you can see over here, this is alpha Fe2O3, which gives a very clear line spectrum. If lanthanum oxide and ferric oxide, they are heated at 500 degrees centigrade, little bit of blurring is there. But if you prepare it for at 800 degrees centigrade, which is a ceramic reaction, then clear-cut 6-line spectrum is obtained. When we prepared it for the co-precipitation method, the reaction was not complete and it was not very clear, you see over here. So, on the basis of these spectral observations, we confirmed that the ceramic method works out to be better. Okay. Now, what is the theory behind it, fundamental science? Here what happens, here again, then lanthanum was replaced with strontium. Strontium is divalent, lanthanum is trivalent. Okay. So naturally, the iron will become in 4+ state. Okay. So how does it work? So we had prepared systems with lanthanum, strontium 0.2, 0.4, 0.6, 0.8 and 1.0. Okay. So here what happens, that main observation was that there is a tetravalent ferric iron cation. This tetravalent cation iron is not so stable in the system, it is very difficult, but here as you can see that we observed it. Then there are oxide ion vacancy and there are some mixed defects. So after complete replacement of, then we will get SrFeO3 and a single line spectrum corresponding to Fe4, so that magnetic field disappears. In lanthanum ferrite, which has a spinel kind of structure, there was a 6-line spectrum. But in strontium ferrite, as you will see, that there will be a and there is an exchange, rapid electronic exchange, Fe3O via oxygen bridging atom. So you can see that this is how from 6-line spectrum to here I am getting a single line spectrum. After having worked over here, completing the 2 CSR projects, when I moved to Roorkee, there I had a friend, Kailash Chandra, who was basically a physicist, but then he had become the chairman of U6 Instrumentation Center. So he said, friend, okay, let us join hands. Okay. So then I had a student, Sonal Singhal, to whom I had said that now she is the head of the department at the Punjab University, Chandigarh. There, some of the systems which we studied was, one of them was NN dialkyl dithiocarbamates. Now here, my purpose was that if we change these alkyl groups, we had prepared something like 25 complexes with different alkyl group substituents, symmetric as well as asymmetric substitutions. So there was one group which were totally high spin in the range of magnetic moment 4.8 Bohr magneton. Then there was another group intermediate spin 3.5 to 4.6 Bohr magneton. A third group of low spin complexes. So just by changing the alkyl groups, whether you call it as inorganic chemistry or organic chemistry, you could get the high spin to low spin to high spin, or high spin to low spin, or there is something like intermediate spin as well. Okay. So So here it is shown a little bit, for the sake of young students, those who are MSc students, just see, you must have always been taught that if it have a Fe3 plus electronic configuration, so if this is less than pairing energy, then this is how symmetrically these 5 electrons they will be distributed. And then if this is very high, then all the electrons they will come down over here, and there will be only a single electron which will be unpaired. But in between there is what we call it as a intermediate spin state, whereby this there will be 3 unpaired electrons. Okay, so this is how these systems are studied, and different kinds of. And here is a plot of delta, that the crystal field stabilization energy, with this G1. So spin crossover phenomena occurs, high spin state to low spin states. Okay. The systems which we are preparing, whether there is a bonding or not, infrared spectrum, up to the low, this 250 range, not the normal 400 range will work, because iron sulfur bonding, that is observed in the range of 208 to 285 over there. So infrared evidence. In order to further observe, we got the X-ray crystal structure done at IIT Madras, only for the single compound, because it costs a lot, and it was found that it is a distorted octahedral kind of complexes which are formed. Now here are the variations of this magnetic moment with temperature, low temperature measurements. You see how the low spin complexes showing no spin crossover phenomena, then high spin complexes showing spin crossover phenomena, then high spin complexes exhibiting spin transition to the intermediate spin, then intermediate spin complexes exhibiting spin transitions. Okay. So all 4 cases, all the compounds, these plots were observed. Here is a typical spectral observations at different temperatures which we observe, and basically there is a 2-line spectrum, but then with the help of computer programs, software available, we had analyzed them to the 2 different sets of quadrupole splittings. So this was my Monswar spectroscopic journey. Overall 3 students, they worked with me, 2 over here, 1 over there at Roorkee. Then when I was working at Udaipur itself, because there were no facilities, so I used to run between Udaipur and Kanpur. At that time, Professor Goel had the lunar samples. He was the only Indian after Tata Institute of Fundamental Research to get a lunar sample. So he said that, okay, you learn this technique, neutron activation analysis. And this neutron activation analysis, first of all, for the sake of young students, I will give you a slight glimpse, that if you have a target nucleus, and if you bombard it with the neutrons, then it becomes a compound nucleus, okay, with mass number additional 1. But this is in an excited state. And when it is taken out of the reactor, it is still radioactive. And because it is radioactive, and because it is in the medium mass range, it emits either a beta particle or the gamma rays, and finally, when it completely decays, it becomes a product nucleus. This technique was discovered by this great man, Hungarian chemist, George D. von Hevesy, in 1936, and he was awarded Nobel Prize in 1943. This technique has the advantage of being the simultaneous measurement of gamma rays. Intensity of different energies are used for the determination of several radionuclides simultaneously. Normally, we determine a single element, say, in atomic absorption. Of course, nowadays, ICP-MS, ICP-OES, they are available as the multi-elemental analytical facilities. But Before that, this technique was developed over the multi-elemental analysis in a single sample. Some people have reported even up to 30, 40. Even we have been able to determine in a single sample something like 34 elements. Okay. Again, just to show it in a different manner, that if you have, this is a target nucleus with atomic number Z and mass number A, it becomes A plus 1. This is in the excited state. Then by beta emission, it comes back to this one. Then and emit. So it is these gamma rays which are measured, okay, and their intensities are directly proportional to the concentration of elements. So characteristic radiations, that is the gamma rays, they are measured, and concentration of isotopes, that is elements, is determined. Oh, sorry. Okay, I have to hurry up. So this is the fundamental equation, okay, which we have used. Then this is a fundamental equation to relate it with the concentration. Then this is the detection limits. Here the advantage is that you have got the detection limits from microgram to picogram, which no other analytical technique has. Of course, nowadays there are better techniques available. Okay. Here is the reactor flux, thermal neutrons, epithermal neutrons, fast neutrons. Then these are the various reactions, various elements, sodium, potassium, calcium, arsenic. Almost all the elements except the lighter elements like carbon, hydrogen, oxygen, nitrogen, etc., they cannot be determined. But the entire range of periodic table that can be covered over there. Here is just a simple methodology. The reactor in the background, this Cyrus reactor, now this is no longer there. The Dhruva reactor is there. Okay. So how the sample is taken, I will not go into the details. This is again a methodology. I will only mention about the two methodologies. One is called instrumental neutron activation analysis, another is called radiochemical neutron. Radiochemical neutron analysis, it requires a lot of analytical chemistry knowledge. Okay. The first samples which I had analyzed, as I mentioned with Professor Goel during 1972 to 74, before going to USA, and there he was involved in the analysis of nitrogen, which was very difficult to be determined. So he used the NP reaction, nitrogen is converted into this carbon 14, and then there was a big kind of system which we had prepared over there, on the basis of which this carbon 14 is converted into carbonate, barium carbonate. Okay. Then 74 to 76, I was fortunate to have worked with Professor William D. Eman at the University of Kentucky, where we had developed a procedure for the rarest elements, zirconium and hafnium, okay, in the various samples, in the lunar samples. The method involved 3 precipitations, okay, and here you could see that this is a zirconium standard. There is a zirconium peak 724 MeV over here. Then in the samples when we see, there is no zirconium peak, you see, but when it is with the precipitation, first fusion and precipitation that was done, then second fusion and precipitation was done, and third fusion, final precipitation, you see these zirconium peaks which were used over there. And for this we needed a high resolution gamma ray spectrometric system. At Nagpur University when I came, I started and I got a DAE project, but the very first study which we did was for the sodium, just 2 minutes, okay. Sodium in leafy vegetables, because we had a americium beryllium neutron source. It has a half-life of, convenient half-life of 15 hours. We analyzed large number of leafy vegetables in dried powder form. This is the system which we had established. Of course, I had a system over here also, but at that time the photo facilities were not there. So this is the system which we had set up at IIT Roorkee, and this is a GM counter system which we use for phosphorus 32 measurements. this is the system kind of how to handle the radioactive samples which we are getting from the reactor after irradiation. So multi-environmental analysis, large number of nutritional and biomedical studies were carried out. The cereals, vegetables, spices, dietary constituents, etc., fish samples, etc., for the environmental samples. Here you see some trace elements have been attributed to various kind of diseases. What happens that these trace elements, if they are in lesser amounts, then there is a severe deficiency, or there is a marginal deficiency, or if they are in the range of adequacy, okay, and beyond that, then there is a pharmacological effect, chronic effect, and ultimately acute toxicity. Okay, so this optimum concentration is very important in the biological samples, especially diets, etc. So because of which several elements like cation has been attributed to selenium, minimata to mercury, ethylite to cadmium, Wilson disease to copper, and like that. But these trace elements, they are not fixed elements. What happens that their concentrations vary with age, sex, diet, geographical, climatic conditions, genetic factors. Okay? So you have to have the proper controls. So in collaboration with a professor of medical surgery in Government Medical College in Nagpur, we had analyzed some breast cancerous patients. Okay? And when they were compared selenium to zinc ratio.
Next session.
Huh?
Next session is there.
Okay. I think the role of elements in breast cancer, it was found, one of the elements was this selenium, which was found to be higher in content. Then on the advice of the editors of biological trace element research, we were advised to analyze these blood samples also. So this is how the comparison is shown over here. You see, tissue, blood, the cancerous and non-cancerous, all that. So they were well correlated. Then they were compared with the diet, and it was found that if your diet is selenium deficient, then you are prone to breast cancer. Okay. Since we had this americium beryllium source, one of the UGC project which I got was for the non-destructive determination of major constituents in ores which are found in this region. Bauxite, which major constituents are silicon, iron, and aluminium. All these three elements can be determined not simultaneously, but without destroying samples. Okay?
You have to skip now.
Okay, yes. So this is the latest paper which I had, because sometimes what happens as a person after having retired, and then during this COVID period, what to do? I just digged into the thesis of my old students. So one Vivek Singh from Nagpur, another was this Chaudhary from last student from Roorkee. So we had used this use of multiple irradiations and reference materials as comparator standards in quality control of neutron activation analysis data of biological samples. Okay, so this is now available online in biological trace element research. Okay. But all the old data. So some of these elements which we have determined was sodium and potassium in 3 different standards which are available. I think I'll just skip this.
We become very late for the next session.
Okay. I think the third area which I had worked was radiation chemistry. Because this gamma chamber was available, various inorganic nitrates they were studied for the analysis reactor. Nitrate becomes nitrite, and then this nitrate can be determined very easily. Okay, so this is the gamma chamber which is still available in our department at Nagpur, and Nirupma Joshi, S.P. Kulkarni, and Nilima Agrawal, they had worked. So we had developed this efficient energy transfer mechanism. So gamma radiolysis of lanthanide nitrates and double nitrates, because they are formed, they are supposed to have been formed in the waste, nuclear waste. So Here is the acknowledgement to my teachers and inspirers, late Professor P.S. Goyal, W.D. Newman, who is also no more, and Professor Nakahara at Germany, this Japan, Professor Ambe, with whom I had a patent. Then my friends at well-wishers at BARC, who helped me a lot to get this decision. Then my collaborators in NIRI, this Government Medical College, ITRC Lucknow, all my students at Nagpur University and IIT Roorkee.
Thank you.
These are the various funding agencies which I have already mentioned. Thank you very much.
Thank you very much, Professor Garg. Just you had the glimpse that the versatility of the techniques, neutron activation analysis, particularly in radiochemistry type of thing, and the various activities that he took during his career. So because we are running short of time and we have a small tea break after this session, and after that we shall be assembling again. On behalf of the organizers, if you have any question, you can interact with him.
Anybody has got any question? I'm sorry, I just somehow took
So
more
on behalf
time in
of the
explaining the basic fundamentals.
on behalf of the organizers, I am pleased to present a small memento to you.
It is my pleasure to get this memento at the hands of.
Thank you. So we will have a tea break, 15 minutes. 10 minutes break is there for tea. Tea is waiting.
He will please what will speak about his introduction. Ravi, please.
Thank you, Dr. Ram, for the kind words. At the outset, I would like to thank Professor Vanjana Agrawal for giving me this opportunity. Today, I'm going to discuss some of the, research finding in the form of short stories, what we have realized at, IT Delhi. As a synthetic chemist, we continuously put our, am I loud enough? I mean, you all can hear me? I think, yes. As a synthetic chemist, our job is to synthesize all right. So as a synthetic chemist, our job is to synthesize library of small molecule, and these library of small molecule works as a feedstock for the nature in nature as a, you can say that for the bioactivity, and that turned out as a drug lead molecule. So that's the continuous generation of small molecule library. That is the one job of organic chemist. And while doing so, we try to tap the natural resources. We take lesson from the natural products. We try to utilize basically the light as a source of energy. And what another aspect important over here is that you're not understanding individual molecules behavior, but in the system as a whole, how does it interact, how does it behave, that is important to know. So synthetic chemist job on these three sub areas focuses, and at IT Delhi in CCSL we focus basically in the three disciplines, sub-discipline I can say that, asymmetric catalysis, CH bond activation, and photocatalysis. So most of you will be intrigued that how this precision comes in biology. Like we all have been taught that log-kill model through which the bioactivity basically that natural system kind of like translate, and there this interaction which defines how this very precisely it is able to kind of like execute. And if we look over, if we go in the detail here, so we will find that nature has its own unique way to do this precision. And because if for each and every response they have to have a individual system, the number of system will keep on increasing. So to reduce that complexity, they started looking over the three-dimensional arrangement in the molecule. And if you look over to exemplify that here, I would like to bring that how three-dimensional arrangement can be sensed in the biological system. You can see here that we all are familiar with the karve seed. We do the dal tadka and spearmint, that pudina. Both have very different unique flavor. And what is different over here? Different over here is that three-dimensional arrangement. If you look over around this carbon, the three-dimensional arrangement in these two molecule is same, only the three-dimensional arrangement is different, and that we defined with the response to the chirality. We need to have that non-superimposability. That's what we have been taught in our. This is why did I bring this example? Just to make you understand that what the science I'm going to discuss, it will be easier to you to understand. And to make the story short, here you can see that how does it happen in the biological system. In the biological system, you can see that active site have, if it finds the whatever the foreign molecule goes for the interaction, if it has proper interaction, proper overlap, then it gives positive response, as you can see here in these three contours. Whereas if the same molecule has different orientation, it does not match to the active site, and that cannot give the biological response. And that's what we can say, that this is responsible. The only biological system can differentiate the three-dimensional arrangement of the molecule. If you look over that drug discovery program, it's a very, you can say that very very costly, and it requires very long time period. You can see close to 15 to 20 years. And it starts, if you look over here, from the researchers, academic researchers who thinks about the kind of molecule we need to design to get the drug lead molecule, and from there various protocols he follows, and then it goes to the approval. It's a very lengthy process, and it requires a lot of financial support. And during doing all these sciences, you may find that many times we end up with the a lead molecule which is a kind of approved or licensed as a racemic molecule as a drug. But if you do the thorough investigation, you will find that only one molecule, three-dimensionally uniquely attached, only one molecule is important for the bioactivity, whereas the other one is inactive. Here I have mentioned some of Janubia, which is the anti-diabetic drug molecule. Only one is active. Lyrica, which was at the UIUC, Scammer did, which has come from the academic lab. And if we look over these business, how much this asymmetry in the drug discovery business, it creates close to $100 billion market it creates. And so very common example, if you see that ibuprofen, most of us have been used at the different stage of our life, and in that ibuprofen, only S-ibuprofen is important, only one. And how is it different? As I told you that they have unique arrangement around the carbon center, that's the chiral center. That's what I'm going to talk about, that how can we achieve that unique, that individual formation of that chiral component? How can we differentiate? We are talking about that only attack from the one site, and that should lead to the only one enantiomer, not to the mixture of. And the principle here again follow the same catalysis principle when we talk about that uncatalyzed reaction and catalyzed reaction. Yes, I'm saying that you need to create a chiral pocket where activation of prochiral center should take place, and then from the specific orientation, nucleophilic attack should take place. As we all know that a nucleophile and electrophile combination leads to the bond formation, and that will lead to the corresponding chiral molecule. So that's what here you need. But however, that difference in the activation energy is very miniature, very small, and that difference in activation energy, if we are able to identify, if we are able to optimize, that can lead to the chiral molecule. What we got interested, we wanted to explore basically vinyl-Lagos reaction. Why vinyl-Lagos reaction? Most of us are well familiar that Diels-Alder reaction is the one reaction where from the simple molecule one can synthesize the complex molecule. You say that butadiene and dinophile as you can say that acrylates, you can get the cyclic molecule. Same Diels-Alder reaction, if you perform in when the diene and dinophile part of a chain, then it gives complex. When we talk about when the diene and dienophile are part of the one ring, then it gives further complexity. What I mean to say, from the simpler molecule one can get the highly functionalized complex molecule, and that's what the vinylogous reaction of silyl ketene is known for. And it's not like vinylogous anones are not like unknown. Here you can see that in nature also this pentacyclic core of rhombine and reserpine was installed by like vinylogous aldol reaction, and we got interested with the vinylogous Michael reaction basically for of the silyloxyfuran and cyclic quinone. Why is it so? You can see here estrigol, tuberferin, number of molecules are there where it is important. Here you can see that to perform that, here we selected like cyclic enone, cyclohexenone and silyloxyfuran, and we were lucky to find that simple chiral primary amines, diamines were very reactive to give that very high enantiomer selectivity. As you can see that reaction proceeds through the bifunctional catalysis. In presence of Bronsted acid is formed the diammonium salt, and that diammonium salt reacts with the cyclic enone and it forms the iminium ammonium salt, and then it interacts with the, you can see that two functional groups are activating at the same time. Both the reactant electrophile as well as the nucleophile are bringing together, and this proximity leads to the sigma bond formation. Not only 6-membered or 5-membered ring, but also middle size ring. You can see that cyclooctinone, octinone and 12-membered and 16-membered, all these kind of enones can be explored. We have also transformed these adduct to the further saturated lactone, as well as we have demonstrated with the very high selectivity nitromethane addition and vinyl cuprate addition. What I mean to say that while performing the regular group transformation chemistry, there is no loss in the enantiomer selectivity. That reflects that how robust these adducts are. Not only this, if you can see, if we do Google search or if we do SciFinder search, we can find there that indoles and chromoens, these are the molecules, these are the basically pharmacophore. Everywhere in the you can say that lead molecules you will find these cores. So how to install directly at the very advanced stage these kind of like core in the small molecule? To do so, one can think that why can we synthesize like vinylogous nucleophile of these kind of molecule, and for that we selected 3-alkylidine isatine where silyl ketene can be easily synthesized, and that in presence of bifunctional catalysis can be, we explore for the ketone here, ketone aldol reaction, and here basically we focused on the like ketone because ketones are unreactive and their controlling selectivity is bit challenging, because in the case of aldehyde, if you see that hydrogen and alkyl group, there is huge difference in the size, whereas in the case of ketone both alkyl group are of similar size. So differentiating the phase will be very challenging. That's what we selected here, sir, reactive ketone, ketoester, and you can see here by trying different kind of bifunctional catalysis, we got that 9-amine quinine thiourea derived catalyst gave very high selectivity, not only reactivity up to the level of like 85 to 90%, but enantiomeric was excellent up to 99%. Here again reaction proceeds through the bifunctional catalysis. As you can see here that both like thiourea activates the acceptor, and that quinolidine core of this quinine thiourea part activates the 3-alkylidine isatine. You can see here that it basically, because of its basic nature, it's a deprotonate and forms the corresponding innovate, and that brings together and that leads to the sigma bond formation and regenerate the chiral catalyst for the next catalytic cycle. We have also demonstrated that these are the reactive intermediates which form in the reaction, and you can see here that we have done the NMR titration where it's clearly interaction of ketoester as well as thiourea. You can see here shift in the C9H proton, where downfield shift is shows, as well as that aryl CH protons, which clearly indicates that there is some kind of interaction we have arrested. We have also shown that in presence of like 3-alkylidine isatine and thiourea basically deprotonates and exomethylene group forms. You can see clearly it generates here. Not only this optimization, we have also done that arrest through the HRMS, high resolution mass spectrometry, that these two reactant get unified through this chiral robot. You can say that this robot basically bringing two pieces together. How do we play the origami? That's why, like, the same way these two electrophile and nucleophile comes together and forms that we have arrested. That data. We also realize this not only for the cyclic quinone, we also realize for the acyclic, as you can see here, because ismidospiridine, copasonone and malagasine, all these molecules, basically carbajoles. And what is uniqueness in these carbajoles, highly packed with the very, kind of like, multiple stereo center in coagulation. There are 3 to 4 stereo centers are there. How to reach these targets? One can reach to these targets by getting this, basically that acyclic product and then cyclize it under the acidic condition to generate these three. Before that, you need to have those chiral center in the scaffold, and then after the cyclization can lead to that. Again, reaction here proceeds through the bifunctional catalysis. As you can see here, the ketoester gets activated through the thiourea, and 3-alkylidine isatin gets activated by the quinidine, and that leads to the reaction. We saw how indole core can be installed on a small molecule scaffold at the very advanced stage by doing very selective vinylogous aldol reaction, vinylogous Michael reaction, can be utilize it for the basically synthesis of chromo-N system. As I told you that these are the chromophore which are very frequently occurred in the medicinal compounds. Because of their unique property, or we can say that if you install these cores in the small molecule, that gives us opportunity of double-sided swords, that okay, if this chromophore will not work, the other chromophore will work. That opportunity it provides. And here you can see that in this case we have is a kind of integrated chromanone system with the indole system through this vinylogous reaction. Yes, I will be really quick, and you can see here that we activated. Here are the some of the kind of like substrate scope. Basically, here we activate the alkyne system through silver, and then under acidic condition, normal Brown state acidic condition, we activate the silyl ketene. Basically, what happens that in situ it forms the isochrominyl cation, and that isochrominyl cation gets selectively attacked by the 3-alkylidine derived silyl ketene, and that forms the corresponding scaffold. You can see here that we were very happy to report very high selectivity. As you can see that Dieter Ender case was able to give only like 2:1, and other from the Spanish group gives like 9:1. Both this paper was published in Engoanti Chemi, and this was in Nature, and we got like 19:1 selectivity for all these cases with very broad substrate scope. We have also demonstrated that this silyl ketene is the intermediate, vinyl silyl ketene is the intermediate, and that basically after the reaction with the Brown state acid gets transferred on the in the form of proton, and then take care of like the next catalytic cycle. So far you have seen that how these vinylogous nucleophile are very advanced kind of source of establishing, you can say that a small molecule scaffold, and that can be further kind of explored to the 3-cyano-methylcoumarine. As I told you, 3-cyano-methylcoumarine is the another scaffold which can be installed by the vinylogous reaction. Either you can talk about vinylogous aldol reaction, vinylogous Michael reaction, vinylogous Manic reaction, so on and so forth. You can do that one, and that's what we want. We realize over here on the maleimide system. These scaffolds are well known, but at the same time, it imposes high level of problem with the selectivity issue. As you can see that maleimide has C2 symmetry, and differentiating the phase is quite challenging because the attack from the any side will lead to the mixture. So you need to fix not only the binding but also the phase. So binding, differentiating within the same kind of functional group has to be differentiated, and that's what, if we are able to do so, as well at the same time if we are able to activate the vinylogous nucleophile, it can install the very high selectivity. We were lucky to receive basically this differentiation of maleimide system and phenyl maleimide system, and there we found that if we have like N phenyl group substituted at the para position, that gives very high selectivity. At the same time, it activate the 3-cyano-methylcoumarine, and here basically the tert leucine derived thiourea. So we have designed different kind of like chiral small molecule as a chiral promoter, or you can say that chiral catalyst, and we do very extensive screening to understand that which one is the reactive. Based of that, like kind of activity as well as the result, that based on that we redesign to look over that what are the guiding factor, what kind of steric or electronic factors are there that helps us in redesigning the catalyst. Here you can see that why I am emphasizing that point, because you can see here the tert leucine derived thiourea was able to give 97:3 enantiomeric excess as well as 98% of yield. And with that we got like very broad substrate scope. This is right now ASAP article, and we have also demonstrated that it can be functionalized without any loss in the selectivity. So whatever the adduct we synthesized, it can be further functionalized. It can be like converted. Not only that, again here as I told you that reaction proceeds through the bifunctional catalysis. You can see that 3-cyano-methylcoumarine, just 2 minutes, it gets activated and forms the corresponding like innovate, and this N-maleamide, N-phenylmaleamide gets activated with the thiourea. These two coupling partner come close to each other. You can say that here catalyst is a matchmaker which brings together the two kind of like not liking each other people, and that leads to the amalgamation and like unification. We have also, you can see here that through the HRMS we have demonstrated that this is the HRMS peak for the catalyst, and then like this N-phenylmaleamide which interacts then responsible for the peak B, and then again with these all. So it's a kind of chiral robot, you can say that which is having like two reacting partners, and reaction proceeds to the bifunctional catalysis. As I told you that in case of N-phenylmaleamide, here like diketones, like 1,3-diketones, basically how to differentiate their like phases, and that's what. It doesn't matter that every time whatever the chiral catalyst you have synthesized will work for your reaction, but the knowledge you receive through that helps you to how to redesign and apply that for the catalysis. That's what over here you can see that we already champion catalysts like quinine derived as well as Takimoto catalyst and tert leucine, which was successful in the earlier example. You saw that tert leucine derived thiourea was giving very high selectivity, excellent selectivity and excellent reaction, but it did not give for this one. Almost scaffold are similar, but you can see here when we increases the you can say that hydrogen bonding capacity by synthesizing the corresponding dipeptide thiourea, that gave again 97:3 in chloroform and very high yield. You can see here that it gave very strong selectivity and the strong reactivity for all these cases without any loss, 96:4. Again reaction proceeds here through the bifunctional catalysis. Basically the 1,3-diketone gets activated by the thiourea, and tertiary amine does the deprotonation to generate the diinnovate, and this diinnovate again attacks, and here what happens that again that innovate, it does not get quenched by the proton. In fact, it attacks on the nitrile and it leads to the annulation reaction. And this annulation, after the you can say that after the rearomatization, it leads to the corresponding kind of aniline kind of system with the chirality. You can see here the point chirality over here, like it gets introduced in the last. So I would like to summarize my talk. I hope I am at time. And so here I narrated 3 Sati stories, and all these Sati stories has some kind of like information. And from the we talked about vinyl-August-Michael reaction, vinyl-August-Aldol reaction, and vinyl-August kind of like Michael reaction of a acyclic system. In the last, I am thankful to the funding. Without money there is no science, and my co-workers, I am standing here because of their hard work. It is very difficult to motivate students, because as he told that very short span of like concentration, 3 minutes he gave. So everybody wants that in first year itself I should complete the 5-year work and my thesis should be there. So I have to motivate a lot to my graduate student to take the tougher problems, because people do not like to do the chiral problems, and that's what, like, but I enjoy doing that chemistry. And in the last, CSIR and DST India and IT Delhi for the startup grants. Thank you very much. I will be happy to take it.
One or two quick questions.
Molecules you prepared. May I know, instead of thiourea, what is the advantage versus urea? Can you compare these two types of catalyst, urea versus
Yes.
thiourea? What that sulfur makes difference?
So basically that, if we look over the acidity of the NH in the urea versus thiourea, it gets enhanced very tremendously actually. So sulfur basically, and also it provides the coplanarity. So it kind of like aligns in comparison to, urea. So that the acidity, when it increase of the NH, that participate very strongly in the hydrogen bonding capacity. So that the quantum, you will get reactivity with the urea also, but that, reactivity will be lower side actually.
Sulfur will reduce the solubility.
Solubility, and basically that, again it comes to the polarity point of view. Sulfur, because it's bigger than the oxygen, so it has better polarizing power rather than that. Yeah. Any more question from the students? Yeah, I will be very happy to take any question from the student.
They will catch hold of.
Yeah, okay.
Becoming a timekeeper is very difficult, So now next I would like to invite Dr. Dalip Kumar. He is a senior professor, Department of Chemistry at BITS Pilani. And he has only one or two, I will refer, Platinum Jubilee Award Lecture, Indian Science Congress 2018, and ISCB Best Teacher Award 2018, and he is a CRSI Bronze Medal holder of 2017. Stage is yours, Professor Dalip. Once again, I will request you, please maintain the time, and you are a professor, you will do that.
Thank you, Chairman, for kind words. And at the outset, I'm very thankful to the organizers for giving this wonderful opportunity to share what, the efforts we are making at BITS Pilani, and particularly, the colleagues and seniors and students, and above that, my mentor, teacher, whatsoever I am, because of Professor S. Singh, it's a wonderful opportunity. Thank you so much, sir. So the efforts we are making, one is you see these natural products which are indole, and other is bisindole type of alkaloids. And here is we are targeting tubulin, and the other type of the anti-cancer entities we are making based on photodynamic therapy. So initial introduction already was given in the previous lectures, so that will be quite helpful to me. And then, like Professor Ravi was talking, that student about thesis problems. So porphyrin is difficult molecule to handle. So we reduced to, let's work on this also. So we are taking advantage of body P as well as porphyrin based photosensitizers. So the photosensitizers, there are several photosensitizers. This is a porphyrin macrocycles, and if you see, there is meso, and these are alpha beta positions. And from porphyrins, if double bond is reduced, then it chlorine, bacteriochlorine, phthalocyanins, and various macrocycles are there, which are very good photosensitizers. But the issues are the which range it absorbs light, and there are solubilities and other issues are there with these molecules, but this is very good base to design. And when we say ideal photosensitizer, so ideal photosensitizer could be high quantum yield, and it absorbs in the red region, particularly this therapeutic window 600 to 800 nanometer, which is quite optimum. And then there is a tissue selectivity, and finally the macrocycle should like a drug-like properties, which can be solubility, lack of toxicity, and good pharmacokinetic profile, rapid and complete elimination from the body. These are the essential requirements for a photosensitizer. So, when we photodynamic therapy, a photosensitizer in presence of molecular oxygen and shine lights, the photosensitizer triggers, goes to excited state, and then through intersystem crossing, it either can be a type 1 mechanism or type 2, where it generates singlet oxygen, which is predominantly, it's involves generation of singlet oxygen that is quite responsible for the killing of the cell selectively. Now, what are the issues with these photosensitizer? Particularly, one is the solubility, and then next is that how the photosensitizer can absorb in this range 600 to 800 nanometer, because you see that the penetration of the tissue in the depth, which is only this red light, is quite optimum for this. So, and then there is the ways that how it the action, the photosensitizer works, that particularly in under oxidative these conditions. Now you see that the drugs in the this is like a meta-hydroxy at meso position. This is tamoporphin and hematoporphin. Chlorine based drugs are there, and then this again this polymeric sodium salt. So these photosensitizer are having the side effects that solubility issues are there, particularly dosage problem is there such with these polymers. So further modification in terms of absorbance and tissue selectivity is desirable. So therefore, what we are doing this recently in this paper, it's nicely it has been documented, these photosensitizers. So what is that? For the porphyrin modification, we are doing that functionalization of this porphyrin at meso position or these two beta positions are free, and this macrocycle upon modification, that it leads to the change in the optical properties. So there are 4 meso position and 8 beta position for modifications, and these are the some advantageous features, that there are various reactive sites are there. One can functionalize, then one can tune the properties depending on the side functionalities, and particularly with heterocycle modification is less explored, and such because presence of heterocycle, one is it provides additional interaction, and other is it changes the electronic behavior of this and donor acceptor terms. So that also gives advantage to this macrocycles. So here we will share that what modification simply we have carried out and what is the advantage of this. Now you see that this aminophenyl pyrrole reactions, and this starting material can be prepared using this triphenyl formyl porphyrins, and simple this Pictet Spengler reaction, this gives pyrroloquinoxylene appended porphyrins, and just TFA toluene, and at this temperature reflux it, one can get this as well as corresponding this dihydropyrroloquinoxylene appended porphyrins. Now with this, having this porphyrin in hand, and subsequently we prepared other quinoxylene appended porphyrins, and this metal can be a free base which is without metal, and also additionally we prepared here this nickel and copper zinc chelated porphyrins, and this type of appended porphyrins, it causes, because it's macrocycle pi-pi interaction leads to aggregation. So here when we introduce this sterically hindered phenyl dietbutyl ring, in that case the solubility also enhanced, and we could prevent the aggregation of these compounds. That is what we have synthesized these type of compounds. And with this appended porphyrin is in hand, next nicely we have utilized them using this various oxidants, starting from this iron based, and then DDQ scandium triflate, and then finally this iodobenzene trifluoroestoxy reagent worked perfectly for us. And in the combination of this Lewis acid 1:2 and versus 0.6 of BF3 etherate leads to this CC bond formation at meso position. So, we are having this meso beta appended pyrroloquinoxylene systems, and we prepared in quite reasonably good yield this compound. So, this is with the metal is nickel, though we tried with free base as well as copper, and the reaction was we could find that in presence of this nickel chelated porphyrin, that is the right the substrate for this reaction. Now, based on this all the appended porphyrins we subjected to this oxidative dehydrogenative CC bond formations, and then this position also be blocked by taking this indoloquinoxylene system, and then again we having this is sterically hindered position at the trans of these porphyrins, and we prepared these good number of these photosensitizers. Now, next is of course, this NMR tells that how upon this formation of this one, this quite distinct proton and de-shielded most of the protons. So, here you see that the interesting part is absorption. Porphyrin generally shows two bands, one is at 418, and then there is a weak absorption in that is the Q band, so above 600. But after the fusion, this is for the appended porphyrin, this one, and the fused one, you can see here with the black is with nickel chelated porphyrin. So, the Soret band was like this one, it has become the splitted into two peaks, and same time it has shifted. It has shown absorption shift to 100 to 150 nanometer, that is what we were expecting. And in case of that Q band, you can see that here significant that band became intense, going from here to here, you can see that. So, now the therapeutic window 600 to 800 nanometers. So, this molecule could be a potential photosensitizer and can be utilized in the photodynamic therapy. This one, it shows that again further that how that this molecule are potential photosensitizer. So, this is diphenyl isobenzofuran, which can trap the singlet oxygen, it undergoes cycloaddition. So, this molecule absorbs at 415 nanometer. So, with the increasing concentration of the photosensitizer, you can see that upon shining light, this absorbance is decreasing. It means the porphyrin is what we synthesize is generating singlet oxygen. Therefore, that this molecule could be a potential photosensitizer to generate singlet oxygen. And above that, you can see that there is different bands and leading near to NIR range 600 to the 800 nanometer. So, this is further the HOMO-LUMO band gap also one can calculate, and you can see that decreasing trend going from this appended to the fused one, the band gap is reduced from 1.84 to 1.31. So, that also is analogy with the band is shifting to the red shift is there. So, just because of paucity of time, I will show just molecule that here that what we have shown is this is the substrate, okay, and this meso beta fusion just we have using this diaryl iodinium salt. We have installed this immunonaphtho the ring system across this meso beta system, and we prepared various the metal as well as metal free porphyrins, and the copper triflate catalyst is optimum for this reaction. But when trace of water is there, in that case, instead of this fusion, there is aryl amidoporphyrin formation is there. And these fuse system, further we have, these are various molecules we have synthesized with having different metal as well as variation in this aryl ring. And here also you can see again the band gap is from 418, it has shifted to close to 467 nanometer, and also the variation in emission spectra. So, in one case is completely the quenched, but the expected the red shift we have observed, and also the band gap is reduced in these systems. So, we have developed two efficient ways to the make annulated system to the core porphyrin macrocycles. So, the next type of what we have done is integration. It is in the natural product itself is known. If you see these strychnine, chlorophyll, as well as this drug molecule is integration of these two. So, these are natural products. So, learning from these aspects the molecules, we have like Professor Tiwari already shared here, this is the standard lead molecule for DNA intercalating agents, and with modification of, because the problem is photocytotoxicity of this compound and aggregation. So, here we have modified one side, and since beta carboline is known to generate singlet oxygen, and this carbohydrate conjugate, it has shown that synergistic effect. So, therefore, we have designed this compound. So, how we have synthesized here is just I am sharing that this final molecule, that this coupling of this tripyridyl aminoporphyrin with this beta carbonic acid, it gives this good yield, but the problematic is here. So, when initially we used to quaternize, you know, there is a mono, di, tri, we used to get a mixture, and sometime it will not fly in the mass spectrum, but when we subjected this to microwave, it fully quaternized, and we got this compound as well as quaternization here. Now, we had this molecule with free base as well as metal chelated, and you can see the activity of this compound. So, it is showing here efficient the DNA cleavage in UV as well as exposure to visible light, and when compared to standard. So, this is just, it is showing the DNA fragmentation, which is it is inducing apoptosis in UV and visible light, this compound. So, the cytotoxicity out of these molecule, we found that this is the best molecule where beta carboline is linking to this position 1 through this amide bond and having 144 nanomolar activity. So, we prepared trizol as well as both type of the compounds, and we found that activity has high, it's when compared to the standard, that is tetrapyridyl cationic porphyrin, its activity is far better than that. So, that is showing 300 nanomolar versus this is 144 nanomolar. Now, we are also working on this natural porphyrin, which is this PO4 this one, and this pyro-PO4. So, this is because of the selectivity to target there for various conjugating with various receptor recognizing moieties. So, these are the in literature known. So, based on this and what we have done is this tryptamine, you see that its conjugation with this natural products also found to show anti-cancer properties. Here this salicylic acid, though it is anti-inflammatory compound, but also it has observed that it is showing anti-cancer activity, and it has been conjugated there, and with this particularly with this chromone tryptamine conjugate, this also was found to this inhibit this breast cancer resistance protein. So, and this alkoxy derivatives are also quite interesting. With this in mind, what we have done is we have taken this natural porphyrin. Natural porphyrin is this one PO4 and coupled with tryptamine. So, this integration, one is when we, because we were not knowing where to conjugate, and in THF at 60 degree, we found that this ring opens up and there is linkage, amide linkage between amine and forms. And when reflux in toluene, this goes to at this position, and this one at this 17 position also we prepared the amide that initially by the hydrolysis and subsequently coupling with the this EDC leads to good yield of this amide linkage, tryptamine and piophormide conjugates. So, likewise we prepared these 6 compounds, and then we initially photophysical studies, that where absorption, you see that interesting is that absorption close to this 700 nanometer. So, these are basic the condition which qualifies for to be a potential photosensitizer, and this one it shows that emission spectrum upon excitation at 415 nanometer. And so, out of these 6 we found that compound number 3, this one which is the showing cell viability study, it shows that good activity. Based on this, we have taken this compound for further studies, and also it shows that cellular localization and ROS studies also confirmed that the localization of the two, one is mitochondria versus lysosome tracker. So, in case of lysosome tracker showed that the image is the good correlation, and so this molecule is localizing close to lysosome, in these images we could find. And here is that how this ROS is generated, that is with the time dependent upon concentration of this compound, this absorbance is decreasing. So, that is what it again shows that it is the targeting cell is through the singlet oxygen generation is taking place. So, here briefly I have described that we have prepared, one is this type of heterocycle fused basic porphyrines, and another is very interesting from the beta cyanoporphyrin we have taken, and we prepared such type of naphtho, and we are working on currently on hydrolyzing this, and subsequent we have free ketone and which we are utilizing for some other reactions. And such type of cationic porphyrin, which also now we found that these are good for bacterial activities, and this work is quite interesting, these ethers, and which are very close to the drug molecule, and further nano formulation also we are exploring of this. So, this is one part of the project which I have shared with you, and all these results are because of these students. We most of the time, as previous speaker elaborated, we keep encouraging them, and it is because of them only we are here, and that is what we are just here to getting your appreciation. So, I appreciate efforts of these students, it is because of them only. And finally, I thank my former students, collaborator, Professor Kavita, Professor Rachna is here, and Professor Tanabe from Japan, Professor Ravinder Pandey, who is leading in photodynamic therapy, and then these funding agencies, their support is always essential, to do this kind of work. And finally, here is BITS Pilani. You are most welcome to visit, and we will look for that wonderful opportunity. Thank you so much for your kind attention. Thank you, sir.
Thank you, sir. Such a nice explanation, because in our place also photosynthesis Dr. Giribabu and group is working, and we have utilized this into solar cell like that. We have gone for photodynamic therapy and those type of systems. And your absorption will look like a phyllocyanine one at whatever you got at 7-1. So very nice.
Thank you, sir. I was looking for a polymer collaborator, so I found here.
One question quickly, because indirectly I am giving 7 minutes more to each speaker. As per the schedule, if we are going, so because it is only 15 minutes, but unofficially with his permission I am giving 7 minutes more. Okay, so it should be minimum 20-minute lecture, so people will be satisfied. So on behalf of ISC, Vikas Kumar Jaina. He is a emerging material chemist, and almost all the young scientists, starting from Nasi to Odisha to so he is the recipient of all the young scientists, whatever we can imagine in India, and he is also fellow of Royal Society of Chemistry UK. So now stage is yours, Vikas. You have to keep the time.
Definitely.
Okay.
So I hope I am audible to all of you. So I thank to Chairman Dr. Narayan for your nice introduction, and also at the outset I thank to Professor Ranjana Agrawal and her team, as well as the Indian Science Congress for providing me this opportunity to share my R&D thoughts with all of you. So basically I am going to discuss about the materials what we develop for energy conversion applications. So I will discuss a little more about on hydrogen. Already Professor Jadhav yesterday has discussed what is the importance of green hydrogen. So with this, I just going to give a brief outline about my group activity. Actually, as a scientist at CSR IMMT, we used to develop some electroactive materials, and we try to conceptualize this material to develop some electrochemical devices for biochemical, electrochemical, and energy conversion, energy storage applications. But here I will briefly discuss about a few related topics to energy, that is for development of materials for electrochemical water splitting, for generation of hydrogen and oxygen, and I will mostly cover that what are the material we develop for oxygen evolution reaction, which is a complementary reaction to hydrogen evolution during water splitting reaction. And if time permits, I will discuss about the importance of oxygen reduction reaction, because this ORR and OER both are very much complementary reactions. So with this, let me discuss about what is the importance of water splitting. That already the importance of hydrogen, no, the next scenario is going to replace all our energy, what we are going to depend upon green hydrogen. So how hydrogen we can produce by greener way? One is your, like we can split the water to get the hydrogen as well as oxygen. Also, if you can provide the energy to water, you can get hydrogen and oxygen. Also, you can combine both to get the water. So in this case, both the reactions, hydrogen evolution and oxygen evolution, is complementary in nature. But when you devise a electrolyzer, in one side hydrogen evolution will take place, in another side oxygen evolution will take place, because both the sides in cathode as well as anode, both the active materials should be essential, because one reaction is quite depend upon the reaction in other sides. So in this case, this oxygen evolution reaction is quite interesting, because it involves 4 electron reaction process, while in hydrogen it is only 2 electron process. So that's why this oxygen evolution reaction is quite complicated compared to the hydrogen evolution. That's why you have to develop some active material which can expedite this oxygen evolution process, so that the hydrogen evolution process will be very much easy during this electrolyzers. So oxygen evolution reaction, why I told that is a quite interesting process, because it involves a few 4 electron reduction process, and also it involves 5 different kind of electrochemical steps, and where there is a bond making, bond breaking, and the electron transport takes place, and ultimately, and that is the interaction of your OH minus to the catalyst surface, that leads to different kind of steps to produce the oxygen. But you can see that this oxygen evolution or hydrogen evolution can be produced by 2 major approaches. That greener way you can produce hydrogen or oxygen by photoelectrocatalysis process and electrocatalysis process. In case of photoelectrocatalysis process, we have to develop some semiconductor material, and it can take place in electrode and a semiconductor and electrolyte interface, where both hydrogen and oxygen will evolve. But in the case of electrocatalysis process, we have 2 different compartments, is anode compartment and cathode compartment. We can collect easily the hydrogen produced and also oxygen produced. So this oxygen evolution and hydrogen can be takes place in alkaline solution and acidic solution. Based on the electrolyte concept, the activity of material will be different. Accordingly, we have to choose the material. And also you can see that fundamentally this water splitting needs 1.23 volt to split to get the hydrogen and oxygen, but it actually does not happen because it requires a lot of over potential. That over potential is due to the kinetics barriers for oxygen evolution reaction, because one side will be oxygen evolution reaction, another side will be hydrogen evolution reaction, and at another side there will be a lot of kinetic barriers which will lead to more potential required for oxygen evolution reaction. In another side also similar case, for hydrogen evolution reaction we need more potential. So in both the reactions, in anode and cathode, we have to supply more potential, which is called over potential. And also some additional over potential required for compensation in resistance due to electrolyte, and also the device leads to give some over potential. So that's why the challenge is how we can reduce the over potential, and we can do the water splitting very close to the equilibrium potential, that is called 1.23 volt. So what is the challenge is there? Because a lot of challenge is there, because the, this is the Vulcan plot which is showing the free energy versus how if the free energy is very close to 0, then this catalyst surface will be very interesting to produce the hydrogen and oxygen. And that's why the most popular catalyst, that's called benchmark catalyst, is platinum. Platinum is a very high cost, and it's not sufficiently available, but that catalyzes the hydrogen very close to 0 potential. And also this in case of oxygen evolution reaction, like your ruthenium oxide and iridium oxide, those are also benchmark catalyst, but also they are high cost and low abundance. So that's why you have to develop and you have to design some material which free energy change should be very close to 0 in the case of hydrogen evolution reaction and also oxygen evolution reaction. So when we got interested in this work, and when browsing through the literature, we have observed that some of the materials like molybdenum sulfide, that has been theoretically established, its free energy change is very close to 0 in the case of hydrogen evolution reaction. But MOS2 has been already established that is good for hydrogen evolution reaction, but it's not good for oxygen evolution reaction. But interestingly, what we have synthesized very nanodots of MOS2 nanostructures, very tiny nanodots like less than 5 nanometer, and we have observed that this tiny nanodots shows very good interesting result towards oxygen evolution reaction. But already many reports have established that MOS2 is good for hydrogen evolution reaction, but not for oxygen evolution reaction. But though it is a very interesting result, and I am going to discuss how it is showing that very good behavior, but and we have synthesized these MOS2 nanostructures and in a different method, like in aqueous method, and this is quite interesting method because we synthesize in waters as a solvent, which many methods are there. They used to synthesize this MOS2 in organic solvent medium. But when you do the hydrothermal synthesis of this MOS2 in organic medium or any organic solvent, that will generate the carbon quantum dots. So that sometimes interferes the electrocatalysis process. But here we have developed this MOS2 without any carbon quantum dots and carbon quantum dot free system. And we have also checked with MOS2 nanostructure for oxygen evolution reaction. We have done a lot of electrochemical work, and we have observed that this MOS2 nanostructure shows a very good activity towards oxygen evolution reaction. And also we have compared our data with the existing literature, and you have observed that its properties quite far compared to the literatures already reported in this direction. So further to understand that, I have collaborated with this is my collaborator Dr. Arkady. So I should thank to him, and he has supported to establish the theoretical calculation, and we have observed that when you synthesize very small nano dots of MOS2, it produces a lot of vacancy and at the edges and vertices, and that vacancy exposes the metal centers, and that metal centers acts as an active center to to absorb this OH intermediate and also make reaction with this OH intermediate, and this reaction is very easy to produce the oxygen. So the generated vacancies and at the vertices and edges is responsible for this tiny nanodot MOS2 for oxygen evolution reaction. So that was a story about MOS2, and further we have also developed some new system how to develop some 2D materials that also show very good properties towards oxygen evolution reaction. So here you can see one paper has published in Nature Nanotechnology where they have developed some hematine. So hematine is nothing, that is a two-dimensional hematite, where you can provide like 72 hours of high sonigation process, and that non-covalent material can be formed like two-dimensional structure with high sonigation energy, and that can be done within DMF medium. And also what we got inspired with this work, and further what we did, we tried to synthesize some hematine, but we have done some different engineering on it. We tried to make some vacancy on hematine, and also that vacancy, and also we have modified some method, and we could able to establish a method of producing very 1 to 2 layers of hematite, that's called hematine, and also we have made some oxygen vacancy on it, and also we observed that due to this vacancy and this two-dimensional engineering produces very good properties towards oxygen ebullition reaction. Further, we have studied that oxygen ebullition reaction. These are the linear sweep voltammetry showing how this hematine, and after the vacancy, oxygen vacancy hematine also giving lowering the over potential, and also we have checked that that is like a trimethylamine, some kind of interesting molecule which is source. When you added to that, we have observed that this activity of this oxygen ebullition reaction is decreasing. So that decreases because what it shows that there is a lot of under coordinated oxygen environment when you do the vacancy of oxygens. That gives a very under coordinated oxygen environment on the surface. So that helps to guide that oxygen ebullition reaction, and also it catalyzes at lower over potential. And this is a very interesting electrochemical experiment that's called rotating ring disc electrode system, where we could able to understand how much the Faraday efficiency of oxygen ebullition reactions, and we could able to achieve more than 95% Faraday efficiency. And these are the system what I discussed about for producing very small nanostructure material and 2D material, but the yield compared to for commercial application is not that high. So we have to develop some system where we can produce more quantity of material. And further, very briefly, I am going to show you that one system further we have developed some rhenium sulfide, that was molybdenum sulfide. Further, we have developed some rhenium sulfide systems, and also what we did, we have done some simultaneous nickel doped and sulfur vacancy. When there is a concerted effect of nickel doping to the rhenium sulfide system and creating some sulfur vacancy, that also enhanced the oxygen ebullition reaction. And you can see that at very lower over potential we could able to get this system for oxygen ebullition reaction. And also we have checked the post catalysis analysis of the catalyst, and we have observed that there is the formation of some oxyhydroxides that really helps and intermediate these oxygen ebullition reactions, and that we publish in ChemCom. And further, what I have already told, that we try to develop some system where we could able to synthesize more quantity of material. Here we have developed some metal phosphonate based material, and here we synthesize some cobalt nickel systems, and this cobalt nickel system we study for oxygen ebullition reactions, and this system shows very good properties, but compared to our previous reports where our oxygen ebullition was being catalyzed by 250 millivolt of over potential, but here it is 300 more. So that's why, but you can, the yield is very high, you can produce a very good quantity of this catalyst for commercial applications, but the catalytic activity is quite lower compared to the previous reports. But that's why what we did, we tried to increase the activity by doing some iron and embedded to this system. So we have taken, previously we have synthesized nickel cobalt metal phosphonates. Here what we did, we have added iron instead of nickel to a cobalt phosphonate system, and this system is really good, shows very good properties, and you can see it is 249 millivolt it catalyzed. So what are the report we have published, that shows very good interesting data. So this is the progress of our oxygen ebullition reaction what we are working in our lab, and you can see we have started our journey in 2016. We have published some paper in SS Energy Letter, and further we have tried to develop some new material and do some engineering on the material, making some vacancy, making some kind of system, how the improvement towards oxygen evaluation takes place. And also we have summarized the activity of our materials with the benchmark catalyst like iridium oxide carbon on carbon support, and we have observed that some of our material shows very good properties compared to the iridium oxide, that is the benchmark catalyst. So with this, I am not going to discuss most on these ORR reactions, because this is one system. I am just going to tell you that one system we have developed one material which shows very good oxygen reduction reaction, and this is, in fuel cell what happen. So that's a methanol tolerant catalyst we have to develop, because in fuel cell, in one side there will be methanol oxidation, another side will be oxygen reduction reaction. But when it happens, methanol passes from anode side to cathode side. So that really decrease the activity of the catalyst. But here we have developed one material, that manganese oxide on graphene support, and we have observed that this is the property. You can see this, the platinum carbon is the benchmark catalyst. When you add methanol, its properties total goes. It is not showing the property of oxygen reduction reaction. But in this case, you can see when you added the methanol, it is not significantly changing the properties towards oxygen reduction reaction. So with this, let me thanks to all my PhD scholars and postdoc scholars and project scholars and collaborators for their kind support to carry out this work, and also the funding agencies for their generous support to do this activity in my lab. And at the last, I thanks to all of you for your kind attention to listen my talk. Thank you all.
One question. Okay. Now, next, as per the theme of this seminar, that women empowerment. So I think today's lecture, first woman will be coming, Professor Neetu Singh. She is at Center for Biomedical Engineering, IIT Delhi, and she is an innovative young biotechnologist award 2013 by DBT. Then Nasi Scopus Young Scientist Award for Women Science 2019. DBT Janki Ammal Young Scientist Award 2021, and SARB, and most important, both Singh and Singh Kapula are here. Okay, so I request you to deliver it. Yeah, yes. Unlike him, okay, you have to make up this time.
Absolutely. Okay, so first of all, thank you so much for this brief introduction. That makes my job a little easier. I don't have to introduce myself. And I would like to also thank Acha, mic chahiye. I would like to thank Ranjana ji for giving me this invitation. I think this is my first attendance at the Indian Science Congress. And this is my first time at this platform, and I'm very excited to see how many delegates we have in this conference. So really, really excited. So what I'm going to tell you today in the next 20 minutes is basically a journey in, when I joined IIT Delhi in 2014, and we started looking at some solutions to healthcare problems, and I'm a trained chemist. One part which was missed in the introduction is that I'm an organic chemist by training, and trying to work in the area of the interface of materials and healthcare. So when I started my lab at IIT Delhi, the idea was, can I use my chemistry perspective to actually have some solutions in healthcare? And that's why I'm talking about rethinking the solution. And by the end of this 20 minutes, what I'll try to convince you is that we don't need newer solutions or newer materials to actually come up with healthcare solutions, rather than we need a new perspective and maybe redesign the old things, right? So challenges in healthcare actually can be broadly categorized into two. One is if we can detect diseases early, and everybody in the world is working on these two areas. One, we can detect diseases early and come up with better prognostics. Secondly, in case the disease occurs and if there is a loss of an organ, can we create those organs in vitro in the lab, and can we replace or regenerate the organs? So we call this area as the drug delivery, sensing, biosensing and things like that, and this one as tissue engineering and regeneration, right? So our lab is also working on these two broad categories, and more specifically we are working on technologies, or rather platform technologies, that can detect diseases early, that can we can engineer organs, and if we can develop new delivery vehicles for better therapeutics. I'm going to give you a quick glimpse of these two and get a little bit deeper into the drug delivery vehicle to convince you that how you have to change the perspective of looking at the problem. For disease monitoring, when we started working, we had a very simple question. Biopsies is very common these days in the clinic. Anyone who thinks that there could be some lump in the body, it could be cancerous or non-cancerous, gets a biopsy done. Once you get the biopsy done, what happens is in the lab, the pathologist actually breaks it down and gets these cells, right? And then they start looking at how are these cells behaving, whether it's a cancerous cell, non-cancerous and things like that. It takes about a week to do all these testings, by the way, so I want you to remember that timeline of 1 week. And also there are very simple questions. For example, how are these cells growing? What kind of drugs will affect them? These questions are not answerable right now in the clinic in a short time span, okay? So now a very simple question is, if we can go from this petri dish A to B so easily and so routinely, can we also go from B to A? That's not so simple. It's actually the part of tissue engineering then. If you're able to go from B to A, that means you can create tissues in vivo, right? That means you can, in vitro. That means you can, instead of one biopsy, now you can have 100 biopsies from the same patient, right? So that precious sample that you have from one biopsy can be created into multiple clones of the patient tumor. That is very, very difficult. However, it can be very impactful. And that's exactly what we wanted to do in our lab. And yeah, I'm not going to get into the details of how we've done this. We have published quite a lot of papers on that, and we have 2 patents on this, a US patent and a European patent. So those who are interested can read some of our work on that. Basically what we have done is we have created these microgels, and we have it's a completely synthetic system where we create the scaffolds, we control the chemistry of the scaffolds to create these artificial tissues. With that, what we are doing is we are using them for drug screening. We are calling them as tumoroid if it's a tumor cell, organoid if it's an organ cell, or just a spheroid if it's a cell, right? So we are using these tumoroids, organoids or spheroids to do drug screening, to look at biomarker identification. We are collaborating with, so these are some of the things that we have done. Instead of cancer cells, you change them into bacterial cells, and now in those micron beads, if you have like say 10 bacteria growing into 100 bacteria, you'll be able to detect them really fast instead of using the standard methods. So standard methods, the bacterial detection takes about 48 hours for low counts or 72 hours for lower counts. So that's why you don't get your reports. You will get a fever early on. Even earlier than 48 hours, and the doctor prefers to give you an antibacterial anyways without getting the testing, because it's cheaper that way, right? So we can actually detect with this technology bacteria presence in 20 minutes if it is a higher concentration. If it's a lower concentration, we can detect them into 4 hours, right? 4 to 8 hours. And this is just because we have now miniaturized the reaction volume to micron scales, okay? So we're using microfluidics for that. We're also using them to look at platforms where we can look at the metastatic potential of a cancer cell. So the biopsy cells that we are taking, now we have a platform where we can say whether these cells are metastatic or not within 48 hours. Okay, this is in collaboration. So this work is in collaboration with ILBS. We are looking at some clinical samples from Institute of Liver and Biliary Sciences at New Delhi. And cancer metastasis is in collaboration with AIMS, New Delhi. We are also working on another work which is using them for primary hepatocytes or liver-like function, not just cancer cells but organ-like function. And this is in collaboration with a company in Spain called BFlow. This is a company interested in drug screening. Sorry about that. So we're using them for making liver on a chip model. With that, tumor is a slightly easier organ, or not an organ, but a tissue to work with. because it doesn't have any functionality, although it's complex in itself. However, if you compare to, let's say, a liver or a heart or a lung, it's a slightly easier tissue, right? If you want to make, so all the technologies that I showed you earlier is just to create an aggregate of cells, if you want to call it. If you want to add functionality to those cells, that it requires way more complicated chemistries or interactions with the scaffold. That's exactly what we have done, and I'm showing you an example of a very simple organ, which is the osteochondral region, which is your bone and the cartilage region. The chemistry or the extracellular matrix of the bone is very rigid, whereas the cartilage is very soft. If you had to create one scaffold, you cannot get this elasticity in polymer terms from the same scaffold. So how do you get this? How do you get this difference in elasticity, difference in the material's properties in one scaffold, and how do you control the cells? We have used chemistry for this, and again you can refer to some of our publications in that. And as I said, I'm a chemist by training, so we have used extensive chemistries which even nature does. By the way, there's calcium in bone, there's phosphate groups in bone, and there's carboxyl groups in cartilage. So we've used those kind of chemistries and functional groups to actually control this and how cells behave. I'm again not going to get into it and skip that part. Let's move to the new delivery vehicles that I'm talking about. So everyone understands that drug delivery is a challenge. We've heard from organic chemists how they're trying to build more and more molecular libraries so that we can get more organic molecules. Remember, organic molecules are going to be hydrophobic. They will not be able to get inside the body, so they need carriers. So nanoparticles, and this is not a problem which has come today, it has been an old age problem, and nanoparticles have been a solution. Liposomes, in fact, are clinically known solutions, right? So if you look at the nanoparticle solutions, there is something called as Doxil, which is one of the success stories of nanoparticle based delivery vehicles. What it is basically just a liposome. Now liposome you all are familiar with, it's a lipid bilayer, and it has this beautiful structure where they've also put polyethylene glycol, okay? Polyethylene glycol is a hydrophilic polymer, and the reason you put that on the surface of nanoparticles or liposomes or anything so that there is no protein adsorption, okay? So this has worked quite well. There's also Abraxane, where they have again put the molecule, the paclitaxel along with albumin, okay? Albumin because they want to resist protein adsorption, right? So these are some strategies which are there. Well, polyethylene glycol has come to our rescue because anything that is injected inside the body will have non-specific protein adsorption, and our body is going to reject it. It won't go into the circulation, so even if you put the drug in carriers, it won't reach to the region that is needed, right, where it is needed. So polyethylene glycol helps that. And by the way, all the vaccines that we have just taken, not probably in India, but the Pfizer vaccine, Moderna vaccine, all of them had polyethylene glycol. And there were news about people having allergic reactions to this, and Moderna came out with a report saying, don't worry, it's just a normal thing. It's polyethylene glycol, and the reaction is because of polyethylene glycol. So it's called as the pseudo, it's called as the pegylation enhances the complement activation, and it's called as the pseudo allergy effect, which is also called the Karpa effect. Now, so PEG is a solution, but it is not a complete solution. We are using it in the clinic right now because we do not have better ways, right? So liposomes are one of the success models, but they are not completely foolproof. They also are very quick integrating. They are self-assembled structures, so any interactions can actually break them, right? So they are not the complete solution. We thought, let's look at nature. Everyone does that. Nature has solution to everything, and nature has a carrier which carries oxygen, right? Nature's own delivery vehicle is basically your RBCs. So the red blood cells carries oxygen. We've all studied that. The way it carries oxygen is of course because of the heme, and there's some inorganic chemistry involved. So let's leave that because we don't want oxygen to be carried. We just want the carrier, right? Now what is that RBC like? From a chemist perspective, the RBC is a beautiful, it's a concave, this disc-like a structure, which makes the fluid, the fluid dynamics quite different, you know, instead of a sphere. If you use these kind of structures, it can flow better. So that is why nature has this structure. So I'm again not interested in the structure, but again, something that we should learn from nature. The size is very large, you know, the size is like microns, which is not good, because the moment I put RBCs, artificial RBCs inside, the body is going to recognize it and body is going to remove it, right? So I would like to bring this into the liposome layer. So or other than that, it's just a polymer. I'm going to go to this slide. It's just a polymer bag, right? It's a polymer bilayer similar to my liposomes. In fact, the lipids are exactly the same, which is there in the cell membrane. And you know, it just beautifully, no protein adsorption happens on our RBCs. They are circulating, right? They're long circulating. So what is it about RBCs that affects the circulation? When we started looking into the literature, we found that, by the way, no protein adsorption is called the stealth property in our field. So when we started looking at the RBCs, we found that there's something called as this CD47. Okay, now this CD47 interacts with the macrophages or the phagocyte, cells which can phagocytose. And what it does, exactly, what it does is, there is something called as SIRP alpha. And this SIRP alpha on the macrophages or the cells which are known to phagocytose, which clears the particles, basically identifies CD47, and CD47 clusters. Clustering of CD47 cells sends a signaling saying this is self, so don't kill it, okay. So what is important is CD47 and interaction of CD47 with the SIRP alphas. So what in the literature people have done is, they knew that CD47 is important, they just put CD47 on the nanoparticle, right. Now again, let's come to the chemistry perspective. If I had to coat a nanoparticle or any surface with CD47, I will not be able to control the density of CD47. If I am not able to control the density of CD47, how can I control the aggregation of CD47 with SIRP alpha? It is never going to work, and that is exactly what happened in the literature. This strategy did not work too well. So what others did, they forgot about CD47 and there was marginal improvement. They just took the RBCs and put it on the cell, on the nanoparticles or whatever, right? RBCs are big, and you will have a large molecule, so you will have multiple nanoparticles. You're not reducing the size then, right? So these are kind of things which were there in the literature, and we thought, why not, you know, when, again, I'm just showing you some literature which was already there with RBCs and CD47. We asked a very simple question. The way we make our liposomes is, we put in lipids, right? We put in all the lipids and then we extrude it and we self-assemble them. Instead of the lipid, if I take the lipids from the RBCs, how will my extruder know whether it's an RBC or the lipid that I've put, right? It should extrude and it should make it smaller. That's exactly what we did, not knowing whether it will work or not, okay? So the idea was, you can take the lipid, remove all the things from the inside, so all the mRNA and all the genetic information, anything that you don't need, the heme for example, remove all of it, make just the lipid membrane, and then extrude it through the extruder, and can you make smaller particles out of it? While you are extruding, you can also put in, now similar to your liposomes, you can put in your drugs, you can put in whatever dyes, whatever you're interested in, right? By the way, again, we've done quite a lot of work on this, and you can read our work on that in case you're interested in getting into details. That's exactly what we did. This procedure, by the way, of breaking down the lipid, the RBCs and taking out the mRNA and all that is known. Biologists have been using it all the time, and they have done that quite successfully. So we just borrowed that strategy. And then we extruded it. We created these nanoparticles of small sizes. I'm going to skip all the data. Of course, all the routine characterizations were done, like the DLS, the zeta potential. The key part was to characterize whether we are perturbing the protein on the surface, the CD47 on the surface. We characterized that by SDS page, and also we did antibody staining, and then did single particle tracking to identify whether CD47 was present or not, okay? And we were quite happy to see that all particles had CD47 intact, okay? They were, of course, there were no protein adsorption, they were quite stable, similar to a nanoparticle, they were biocompatible, you know, and we also did immune compatibility studies. For example, can they activate some immune response like TNF alpha and IL-6? It was slightly lower, slightly higher than the RBCs, but in acceptable ranges, okay? So with that, the drug loading, it behaves just like a normal nanoparticle, the drug loading. Here the problem was that it was very fast releasing, okay? There was no control over drug release. In the second version, second modified version, we have a way of controlling the drug release as well. Just wanted to show you that we compared it with the liposomes. This is the gold standard is liposome. We did a comparison with the liposomes and the RBCs, nanoparticles, and we found that ours were slightly longer circulating, ours were more stable. These NV, we call them as nanoerythrocytes. NEVs were, and they accumulated in the tumor more. With that, we started looking at, can we do analyze if they are efficacious, right? Where can we load drugs and can we see if can be used for drug delivery? And these are just some strategies where we, as I mentioned to you, we also optimized the release profile. What we did was we put the drug in a micelle and then extruded that in the system. And that way, the drug had a double diffusion barrier, so it was able to slowly release out of it, okay? So we were able to control the release profile. Here's the data where we injected this, and you see here, we injected these NVEs with the drug. We did not see complete cure of the tumor, okay? It was not perfect yet. As you can see, after maybe 14 days, the tumor starts to grow again. This could be a dosing issue. However, we saw a little bit of toxicity also. So, we started looking at, fine, it could be dosing issue, but how much can you dose? If you're going to give more dosage, is it going to cause toxicity to other systems also, right? It's got a toxic drug in it. So when we started looking at the toxicity, we found that everything looks good. However, in the intestine, our nanoparticles did have some toxicity. What it means is that you have to lower, 4 minutes? Yeah, I'll be done. So you have to lower the concentration of your drug somehow, right? So this strategy, what we did was, now that we're using it, can we use lower concentration of the drug and maybe use some other therapy? Or so it is also called as the dual combination therapy, chemotherapy as well as radiotherapy or something like that. Can we use dual modality of therapy and have lower dosage of both so that we can get synergistic benefits? And that's exactly what we did. Now that we can load things here, we loaded ICG, which is, we just heard about photodynamic therapy and photothermal therapy in this case. So you could use that in these systems also. And we found that, of course, all the basic studies were done. We found that at half of the concentration of the drug that was used in the previous study, we were able to see slightly better result. Again, I would not say that we've cured the tumor here. The tumor is still growing, so we are still working on modifying the system more, but it is getting, it's slightly better than what we had earlier. So this is another version of that whole thing. So with that, I hope I've been able to show you that we didn't really need to make a new nanoparticle. We just re-engineered RBCs. We just looked at RBCs from a different perspective and make them into a synthetic, similar to a synthetic particle. With that, we were able to show that, you can use them for dual therapy, you can use them for regular drug delivery and all that, right? So this is just a small proof of concept that you have to look at it in a different way. Moving forward, we are not, as I said, we've just started. The whole journey is just 6-year-old with this work. So we've just done the proof of concept. What we would like to do is, we would like to actually compare it to different particles which are already there. We've already done with the gold standard liposomes, but we would like to study it more. We would like to look at how it behaves in larger animals. We would like to look at what happens to immune response. So we've looked at the TNF alpha and IL-6, what happens to antigens which are present on the RBCs, is it specific to a certain blood type and things like that. There are a lot of questions that needs to be solved here. So we would like to do all of that now. Only then we can move to, some good relevant preclinical data. With that, I would like to acknowledge all the work of my PhD student, Sahil Malhotra. This is his PhD thesis, and the other work that I talked about is the, few more students' thesis, and IIT Delhi for support, IYBA and DST Nano Mission and DBT Nano Biotechnology Task Force, which were funding my lab in my initial years. And recently I got the SERP Power Fellowship, which is giving me a lot of visibility with women in empowerment. We're talking about that. It's giving me flexibility to utilize my funds and also people know me all around, so that's a good thing. And also Janki Amal Women Bioscientist Award, which again has given, this is from DBT, which is giving me a lot of visibility. So with that, I would like to thank all of you for patiently listening to me for 20 minutes, and I hope I've convinced you that you need to actually look at it from a different perspective, from whatever expertise you have. I have a chemistry expertise, so I've been looking at my problems with that rather than just making new materials and not taking it to probably next levels, because it takes time. It takes 20 years to start from a material, completely new material, to clinical applications. So yeah, thank you.
Thank you. Any one question?
No
So
questions.
just you have
Oh,
seen
he has one.
How does it differ from plasma therapy?
How does it differ? Yeah, so plasma therapy is mostly used for the antibodies that are present in the plasma. They don't actually create any nanoparticles, but you're right, it could be probably similar to that. The way I'm thinking of it is you take the patient blood so that you don't have any reactions, and then you have this extruder kind of a thing in the clinic itself, and you just inject it to the patient, But I don't know manufacturing and all that, I've not thought about it, but probably similar method for the clinician, but the difference is you're not using antibodies. In plasma, it is the antibodies. Yes. So we are not going to inject it in the tumor. This is for the IV injections. No, in the studies also it was all IV. We've done. Yes, absolutely. The advantage we have is, so they actually don't look like, they just have the surface of the RBC. The size is nano, right? And that is why the RBC CD47 does not allow the proteins to get adsorbed, so they become longer circulating. If you notice, I've skipped it faster because of paucity of time. If you look at our biodistribution, most of it goes to the liver. So the body is taking it as dead RBCs. So it's clearing it out slowly, but I'm not saying that it is there like RBCs are there for 15 days. Every 15 days probably you'll get new RBCs. But this is getting cleared in maybe 3 days or 4 days. Liposomes get cleared in 2 days. So that's the advantage we are having.
Would it possible to having association with an nanorobot for releasing, for delivering and repairing?
Yeah, it would be wonderful. We could use some, magnetic particles. People are doing that, and
In order to replace the manual one.
absolutely, absolutely. You can just move it around. Yeah, that would be fun. Yeah.
So very nice work, but you
Thank
have
you.
shown that challenges whatever you
Yeah.
are going to have, starting from drug delivery
Yes.
to how you are going for personalized medicine. So this is a timely project, and we wish you all the best.
I wish we had the hydrogen thing in the drug delivery, right?
So we wish you all the best because
Thank
you
you
are
so
doing
much.
wonderful work.
Thank you.
Go ahead. So you will make one personalized medicine, and whatever robots he is telling, it will be searched, so it will a specific target to that place.
Yes,
So we will wish you
absolutely.
all the
One
best.
day maybe we'll be able to do
Yeah.
that. Thank you so much. Thank you. Yeah. Thank you. Thank you.
In that challenges. So now our next speaker is Dr. Prathama S. Mankar. So you have seen the challenges in healthcare. Now she will be coming with solutions in healthcare. So she is senior principal scientist at CSIR IICT Hyderabad, and she is fellow of National Academy of Sciences, CRSI Bronze Medal 2023, National Tech Excellence 223 TDB, CSIR Technology Award twice. So she is a technology woman that whatever challenges she posed, now each dose of vaccine carries 15 mcg of CSIR ICT technology, and she has been a part of that development in the corona time. So the adjuvant molecules. So with this introduction, I request Prathama to present her work. Mic.
Thank you, Dr. Ramanuj. That was a very kind introduction, and I would like to thank the organizers of 108th ISC for giving this opportunity. What I am going to present today is the work that our team has done. It is not my individual contribution. So whatever is seen over here is from a team that.
Yeah, it's fine. You are loud.
No, please ask him. नहीं आ रहा है. Hello? नहीं. Hello? Oh, ऊपर ही लग. Hello? ठीक है. So this is the work of a team that has been working in CSR ISCT. So all this time you have been listening to the basic sciences, but what I am going to say is something that we have worked on developing technologies for molecules which have commercial importance. Echo आ रहा है? Echo आ रहा है? No? मुझे आ रहा है. Okay. So what we have done is we have tried to develop processes using indigenous chemicals that are available in and around Hyderabad, because Hyderabad is a pharma hub, and within the country, so that we don't have to depend on imports. And then this is my title, that integrating raw materials and atom economy. So this is in alignment with the theme that we have for science and technology for sustainable development. So the basic idea of our processes was to become Atmanirbhar. Atmanirbharta doesn't mean that we should do everything ourselves, but whatever we do, we should do it in such a way that there should not be any competition for us. We should be the best in the world for doing that. And that should be achieved by doing cutting edge research, quest for quality. Quality is always the supermost thing for developing technologies. Then we should have better cost effectiveness. Our technological capabilities have to be the best in the world. Then we have to reduce delays due to infrastructure or procedural problems. And then we have to work with the world from a position of strength. Since all the students have left, I think this slide makes no sense, but when anybody says that chemicals are always the polluting things that we see in the world, that's not the truth. All our life, from morning toothpaste to night sleeping time, when we use a mosquito repellent, everything is covered by chemicals. So I'll skip this slide because there are no students in there. So by a rough estimate, around 80,000 chemicals are in use, and if we as a country think of developing all the chemicals indigenously, it's not going to be possible. So we'll have to take a look at ourselves and decide what chemicals we can develop indigenously. So basically these are the categories. They are petrochemicals, basic inorganics, polymers, specialty chemicals, consumable chemicals, which are the major things that are being used as in the our day-to-day life. And when we come to Indian chemical industry, we have bulk chemicals, which are the major part of the chemistry that is developed in our country. Specialty chemicals are next. Petrochemicals contribute a lot. Fertilizers and pharmaceuticals come next, because our country is a society based on agriculture, and we are leaders in pharmaceutical industries. These are the two industries which need lot of chemicals, which come from bulk and specialty chemicals. So to have an Atmanirbharta in pharma industry, though we are the third largest by volume, we account for the 60% of the global vaccine, which has improved slightly more now with the present pandemic. We have gone up to 70-75%, because most of the vaccines that we have developed in our country were supplied to the world. We do have trade surplus, and the advantages that we have is we have the best and most approved US FDA plants in our country, which is better than even many other countries. And lot of ANDA and IND applications happen from India. So I just skip this. So what we have to do is we have to develop new KSMs, important KSMs for the pharma industry. I'm speaking from the perspective of pharma industry because my expertise in that, but it applies to the agrochemicals as well, because similar chemical intermediates are used for agrochemicals. So we have a lot of facilities which can make GMP as well as closer to GMP facilities. Then we have the capacity to file DMFs or ANDAs. We have Indian pharmaceutical companies were expert in challenging the patents. So that's something that is very well known in India. And we have also developed expertise in developing formulations for the APIs that are being made in our country. So this is third in terms of largest and 13th in terms of volume. Indian pharmaceutical industry has really changed the world's perspective of how to use the pharmaceuticals, and the COVID pandemic has really pushed us into a leadership position. Everybody is looking at us as leaders. So where do we get all the chemicals? So this is a very crude slide maybe, but petroleum industry is one which is contributing to the chemicals to us. So when the crude gas is separated, we get olefins and aromatics. Aromatics form the BTX industry, so we get benzene, toluene, xylene, so that's the BTX industry. And then you get ethylene, propylene, butadiene, which go into other applications. So this is just an example. Where do we get our paracetamol from? So benzene gets nitrated to nitrobenzene, and on reduction, this is a typical reaction where nitro to hydroxylamine, and then it forms the paraminophenol. And all these reactions are being developed in our institute, and we have developed this and demonstrated to the industry. I am not a part of that, but a team from ISCT has done that. So, sorry. These are some of the key intermediates that are being used extensively in the industry. So I have just tried to explain how they are formed. And another source of getting the chemicals is from coal industry, where we get the one carbon unit which can be extended into making other intermediates. So what I am going to talk about is this 5 molecules today, and a bit about the Covaxin adjuvant that Dr. Ramanuj mentioned during the introduction. So tapentadol is a molecule which is used for pain treatment, and it's a feeling that its treatment, chronic pain. It has advantages that it is not causing dependency on the molecule, because morphine and other molecules cause dependency and people get addicted to them, but tapentadol is found to be not giving that addiction. So when we look at the activity of how tapentadol came into being, it started with morphine, and it was found that this is the region that is giving activity, and that's the pharmacophore for making the molecule active. So morphine led to codeine, codeine led to another molecule called tramadol, and that led to tapentadol. So when we look at the synthesis that are reported in the literature, they all start from acyclic intermediates, and then the molecules were synthesized. So we thought that why should we go to an acyclic intermediate, but rather than look for something that is easily available, that's thiopyranone, because it has a ring. When we do the next reaction, it is giving us a diastereoselective molecule, and this molecule is available from acrylic acid, and as I showed you before, it is coming from the petroleum industry. So we have a source for making the thiopyranone using hydrogen sulfide and acrylic acid. So this is how we have done. This is done on a 100-gram scale. So this is a technology that is ready with us. We have filed a patent. So thiopyranone we have made the amino derivative, a Grignard, and then we got this selectivity of 8:2. Ranenical reduction gave us the molecule which we can resolve to get the histamine. The next molecule is alpha lipoic acid. Again, this is a very important molecule, especially it's a nutraceutical, and our country does not make it. It's always imported from China. And there is a small story about this. Customer asked us to develop a technology for lipoic acid, and the starting material, that is the 6-set dichlorooctanoic acid, was coming from China. And when we started working on that, and the target given to us was $80 per kg, and the starting material was available at $30 per kg. So we developed a technology, and we could make this molecule from the dichlorooctanoid within $45 per kg. So the customer was happy, and we thought that we have developed a technology, and when we are ready to give the technology, the Chinese market realized that we have a technology, and the cost of the starting material changed from $30 to $60, and the cost of the final product from $80 became $60. So we had to do a lot of reverse engineering, and this is what we have done. So we had to go back literally to the benzene and then develop a technology for that. So benzene gives cyclohexanone, which on oxidation gives benzene gives cyclohexane, and then it gives cyclohexanone, which gives hexandioic acid, which we convert to dichlorooctanoate here. And we have developed this process for making from dichlorooctanoate to lipoic acid. So this is how we have been developing technologies, because we have to really go backwards to sources that are available within our country. These are the 3 molecules that we have worked on during the time of the pandemic, that was in the first stage of the pandemic. So hydroxychloroquine, favipiravir and remdesivir. So diethyl malonate, 2-ethylamine, ethanol and 5-chloropentanone, all are the key intermediates. And diethyl malonate from chloroacetic acid, again this is available in India and comes from the methanol, that is C1 chemistry. 2-aminoethanol from ammonia with ethylene oxide. Ethylene oxide again comes from ethylene that we get from petroleum industry, and 5-chloro-2-pentanone is synthesized from diethyl malonate. So we could develop a process for making hydroxychloroquine, and then we could trace back how we can make it, starting from the chemicals that are available within our country. Favipiravir is a big success story, because at that time in the first phase we had to develop a process for favipiravir, and this was the this was the challenge given to us, and I am very proud to say that our team has worked on this molecule, and within a challenging time of 23 days we have developed the process and transferred to Cipla, and they have started making favipiravir molecules, and they were given DGCI has approved this molecule for experimental restricted clinical use. So what we have done is we have taken diethyl malonate, as I had told you that we are having it within our country. Chloroacetyl chloride is available with us. We have made sure that we don't lose any atom that was critical for in this, and then all the atoms have been used to get favipiravir, so there is no loss of any atom. We have filed this patent, and then this process has been transferred to industry, and they have made it on tonnage scale. So this is something that CSR has appreciated our work, and we have got the CSR Technology Award for the year 2020. Remdesivir is another molecule which was considered in the phase 2 of the pandemic, and the problem for remdesivir was the starting materials were not easily available. So the key raw materials were ribose. Ribose comes from sugar industry, more from the fermentation industry. Furan, and pyrrole were the starting materials for making the intermediate, and they come from petroleum and sugar industry. So we have developed these processes for making all these intermediates and then coupling, and our methodology has made sure that we get the selected required enantiomer in the better ratios. This is a small story about covaxin adjuvant, and since most of you are chemists, I would like to tell this. Bharat Biotech approached ISCT and gave us a structure of a molecule and said that we want you to develop a process for that. It's just a structure, no technology, no procedures, nothing. So we had to work from scratch, and during the pandemic most of you are aware that we had no access to any chemicals basically. So we had to literally look into the industries around us to see what they have that we can make it into the molecule. So that's how our work started. We developed a process, then we realized that this process we have been using some chemicals like palladium catalyst and others, which were adding to the cost, and they were not making it scalable. So we reworked the synthesis and made sure that we removed all those problems, and this molecule has been made now on kg scale regular basis, and any one of you who has taken covaxin has this molecule in your blood, and this has added to the activity of covaxin. The activity of covaxin almost doubled to just taking the virus and making the vaccine. So this molecule makes a lot of contribution to the activity of the vaccine. So, adjuvant, yeah. So it's an adjuvant complex they make with aluminum hydroxide. So this also was appreciated by CSR. We got a CSR Technology Award. So these are the 5 molecules that we have developed using chemicals which are available in and around us. None of them have come from outside. So this is our contribution to Atmanirbhar Bharat, and as Mahatma Ji said that we should develop something that will be the best in the world. So this also has been patented, and as you all know, our Prime Minister also took a covaxin injection, so he also has our technology in his blood, and This is what are our contributions, and at this point I would like to thank Dr. Chandrasekhar, now DST Secretary, but earlier our Director, Dr. Raji Reddy, who was in our, we as a team worked on these molecules to make these things a success. And thank you all for your attention, and I hope I have not crossed the line.
You are perfectly on time.
Thank you. So, before Ramanuj starts saying something, our campus is as beautiful as Nagpur University is. So, please visit our institute, and you are all welcome.
You can see the sunrise, sunset, probably all points are there.
I tried to cover everything.
Very nice. So, any question?
From alkene that Piccoli acid that is what. So that this dichloro earlier you were buying from the China, right?
Yeah.
So that one cost like it was. And how were they synthesized that dichloro?
Same.
So what do you pass like?
But they were taking adipic acid. He came to adipic acid from
the.
So we had to go back that much so that to make the process accessible.
Most important, it was in a time when raw materials was not available. So you can discuss. So many compliment to you, Dr. Prathama, and your team
Thank
for
you so
working
much.
wonderfully well for our country at that too, because I was he's a student food giving party team. Okay, so I know the trouble that 90 students and with 6 scientists and analytical support, 2 technology within the span of 64 days. So that was the leadership of Dr. Chandrasekhar, Prathama, Raji Reddy, then Purna Nagendra and all persons were there, Dr. Jagdish.
So all this is teamwork, it's not individual work.
So thank you that one has given the challenging problem, you have given solution. Both of you joined together and
That's
you
women
bring
empowerment.
it
That's a woman empowerment.
Okay.
Challenging and opportunity. Excellent talk.
On behalf of Plenary, so now another variety will be added to our program, that you have seen the women empowerment, societal problem to material science. Now we are going to, but lot of people will show the publication. So we have a industry expert, industry turned publishing type of system, Nirmalya sir, that he is at the NISPER. So he will be talking to you about the publication. He has experience in the industry. Then he moved to the pharma, sir, no? You are working in the pharmaceutical science, that he is alumna of IIT Kanpur. And then NISPER was lucky enough to get IIT Kanpur and Bombay alumni. And then NISPER was lucky him to find him as a associate subject editor. Now he is the full editor of Indian Journal of Chemistry. So stage is set for you. So that how to publish, what are the challenges. So he will be talking on to that aspect.
Thank you, sir.
पीपीटी है सर, अभी है नहीं है सर, इसमें नहीं है, फोल्डर में है नहीं है सर, फोल्डर में है क्या कोई पीपीटी? फोल्डर में अच्छा लेके चलेंगे तो फिर इसमें आ जाएगा नहीं, हमें स्क्रॉल डाउन करना पड़ेगा सर आपको। अच्छा पीपीटी मेरे पास तो है, तो से लेके आऊँ? हाँ चलेगा। इसमें मैडम ने कॉपी तो किया था, नहीं किया है, नहीं है मेरे पास अभी है, ला लीजिए ना हाँ सर।
Particularly, I am very much grateful to Professor Ranjana Agarwal, who also happens to be the director of our institute. My talk is slightly different from what you have been hearing till now. It is about chemistry publication. So we have our institute, which is one of the constituent institutes of CSIR. It is the National Institute of Science, Communication and Policy Research. It's
it's an old as well as new institute, as you will come to know. And we publish a number of peer-reviewed journals from this institute. This is our building. It's a beautiful campus. If you have the opportunity to visit Delhi, please have a visit to our institute also. As I said, it's an old as well as new institute. Our history starts from 1951 as Publications and Information Directorate, then 1952 Indian National Scientific Documentation Center, and these two merged in 1996. In 1996 PID was upgraded to NISCOM, and in 2002 NISCOM and INSDOC merged to form NISCARE. And in 2021, that is exactly last year, NISCARE and NISTADS merged to form CSI NISPER. And our mission is to promote communication in science to diverse constituents at all levels using the most appropriate technologies and provide technology and knowledge services to the scientific community. We right now publish around 16 research journals in various fields, and these are all peer reviewed, globally recognized on the genuine CSIR platform, and they have a mix of national and international representation in their editorial boards, and they are included in most of the reputed indexing agencies, and we have online submission and publishing. So we have as you can see, it's a colorful bouquet of all the journals, and some of them are even in niche areas, like for example, fiber and textile technology, geomarine science, etc. And of course, the chemistry, physics, etc. are all there, mainstream. These are the list of the journals, what we have seen in the colorful covers, all the listed. We have around 5 monthly, and the rest are bi-monthly and quarterly journals. And we have a very team of skillful editors who run all the journals. The last current journal metrics we have from 2021. As we can see, we have the journal citation reports, the Chicago journal reports, H-index and NAS index, etc. for all the journals. Particularly for, since I am from the chemistry, so particularly for Indian Journal of Chemistry section A and section B, as we can see, it was 0.412 for Indian Journal of Chemistry section A and 0.456 for Indian Journal of Chemistry section B. Now the new initiatives since last year is that all the research journals have been brought on the online system. Editorial board restructuring is an ongoing process. Earlier we had only editors from our institute. Now it is becoming more broad-based. We have a system of having chief editor, executive editor, and editorial advisory board, etc. And what we have also done is, as far as chemistry is concerned, we have undergone the merger of Indian Journal of Chemistry section A and section B. Section A used to cater to inorganic, theoretical, analytical chemistry, and Indian Journal of Chemistry section B used to cater to organic and medicinal chemistry. So for better synergy, these two have been merged. And of course, we bring out special issues on contemporary relevance. And another thing what we have done is we have started assigning DOI to all our published articles, which was not there previously. Indian Journal of Chemistry started its journey in 1963. In 1976, it was bifurcated into section A and section B. As I already mentioned, section A inorganic, bioinorganic, etc. And in Indian Journal of Chemistry, section B organic and medicinal chemistry. And 2022, again, we have started a new journey. Indian Journal of Chemistry section A and section B have been merged to get better synergy. And so now it covers the ambit of all the topics of chemistry. Section A and Section B, you can see the rankings, etc. And now the Indian Journal of Chemistry has been reinvented. So, as per the policy decision of a high-level committee set up by CSIR headquarters, we have a target of having a premier bioscience journal, a premier chemical science journal, and a premier physical science journal in our institute. So, the chemistry journal has to serve the larger international community and to strongly appeal, have a strong appeal on the international platform. And we wanted to have a global outreach rather than confined to a regional area, either India or South Asian region, but it should be global. And Indian Journal of Chemistry will be premier chemistry journal covering all aspects of chemistry which were covered earlier in 2 separate journals which I mentioned just now. So, we have the publication data for Indian Journal of Chemistry Section A and Section B since the last few years. As we can see from the last decade, there have been ups and downs in their both their receipt of papers and publication, as well as the pages published, etc. And we have the inflow of papers. We see that the inflow of papers peaked for both the journals around 2015 and 16. After that, there was a decline due to various reasons. And therefore, with the new merged Indian Journal of Chemistry, we expect Corona is probably one of the created the mischief. And there has been a turnaround now. And if you look at the country-wise publication of IJC Section A and Section B, it's quite interesting. Obviously, India contributes 64% for IJC A, and for China is the second one. And I think the third one is Iran, probably, yes. And the other countries, of course, they are all listed here. Similar story for IJC B. India has a bigger chunk here, about 82%, and then followed by China again, and Italy, and so many other countries. So it's quite interesting. Of course, apart from India and China, we have other countries also contributing. We have the impact factors for the last decade. Because of Corona and related issues, our content is not what it used to be. So we have a decline in the impact factor of our IJC A particularly. We see a big decline. IJC B is just moving along. Since we have restructured the journals, so our expectation is that we will have better profile now as far as impact factor and other indexing parameters are concerned. Special issues have been brought out from time to time, particularly as we can see for IJC A since 2010 to 2020 in the last decade. Quite a number of special issues, quite colorful. And for Indian Journal of Chemistry Section B, we have issues brought out in 2010, 2018 and 19, very colorful, very impactful. And the important things to remember is that whenever we brought out the special issues, our impact factor also jumped substantially. And when we do not have the special issues, then our impact factor is, again, it comes down. So it is very important to have special issues. Now we have the rankings of our journals. Say Indian Journal of Chemistry Section B, Indian Journal of Chemical Technology, which is our own in-house journal, Indian Journal of Chemistry Section A, Asian Journal of Chemistry and Journal of Indian Chemical Society. So of all these, Journal of Chemical Sciences actually tops the list. There is co-publishing with Springer. and their impact factor was 1.95. So there was a discussion on whether co-publishing does help, but we have it's quite, there's a conflict here. If we look at number 6, Journal of Indian Chemical Society, that's also a co-published journal, but their impact factor is 0.243. So co-publishing doesn't help actually. What helps is the content of the journal. So if we invite more and more better content, invited authorship, or eminent authors and so on and so forth, and people give their best work to our journal, so the impact factor will increase automatically. So content is most important rather than going for co-publishing or other kind of jugglery. So we have the online editorial management system also. This is the process which I think most of you are familiar with fresh submission, then initial scrutiny, then assignment to the referees, and there is also provision for direct rejection also, and then from the referees it goes, the reports are received since it's peer reviewed, and then depending on the reports there is rejection or major revision, minor revision, so forth, and then it comes to editing and then acceptance and then editing. And it's not that only it ends there. We have lot of work after the papers are accepted. For example, we have technical editing, style editing, illustration processing. That's very important because our illustrations and other text, everything should be legible. It should not be like something, because of the poor illustration quality, sometimes the beauty of a paper gets destroyed. So we have to be very careful about illustrations. We always tell our authors that please send your illustrations in the proper format, in very clear and legible form, so that it gives beauty to the article as well as beauty to the journal also. And then the edited manuscript is sent to the author for retyping or recorrections. And then the retyped manuscript is received by the editor and checked once again for journal style, units, which we normally follow the SI units, nomenclature. For example, for chemical names, we use IUPAC, data presentation with respect to text, tables, figures, etc. Then we have, after this processing, we call it what we call the press ready manuscript, and only that is then sent to our desktop publishing. Without these press ready procedures, it is unacceptable to publish the manuscript, and so that it becomes an article. And then we have the first format, or what we call in our common language as galley proof, goes to the author after being checked by the editor. And the galley proof comes back with corrections, whatever the author feels are relevant. And then the second format is then created. The second format is different from the first format, is that in the second format, all the figures, tables, everything, they are fixed and composed in the pages. So page composing is there. Again, it goes back to DTP for page composing. And finally, the articles are paginated and the contents are finalized. So this final issue is given to the press. The online version is uploaded and also shared with all our indexing agencies like Larivate Analytics and so on. And then printing, binding and postal dispatch for the hard copies. Online version has already been uploaded. So basically this is a very long process and it is quite challenging for us. So in the restructured journal, we have already made these changes, that the editorial board, earlier it was not multi-tiered. Now we have a multi-tiered structure. Our chief editor being Professor Govardhan Mehta, he doesn't need any introduction. Executive editor is Professor D. Ramaya, he former director of NIST Trivandrum. Former director of NIST Jorhat, yes. He's very kindly consented to be executive editor. Then we have 12 subject editors, some of them are in the audience right now. Editorial board members, and then Professor Ranjana Agarwal, of course, she's the director of our institute. She in fact took the initiative and it has gone very well. and we have a team of scientific editors, 3 of us in fact. Without them, I'm actually nothing without these people. I am of course there. Then Dr. Pushpanjali and Dr. Sandhya Lakshmanan, she is there in the audience right now. And of course, the role and responsibilities, our chief editor of course will act as a mentor, executive editor for day-to-day functioning. Subject editors will assist the executive editor for reviewer search and for peer reviewing process to accelerate the peer reviewing process. And scientific editors are of course there for the latter part of the processing. And so for the new journal, as we can see, the cover design has been completely changed, and Coden, ISSN, all these we need when we launch a new product. With the Registrar of Newspapers of India, we have maintained the continuity since 1963. We were in correspondence with them and they have agreed. And discussions in progress with Clarivate. Clarivate has already recognized the new journal, and for the other indexing agencies it's going on, and we have the URL of the journal of course. So it's on free access, by the way, on online. Online is free access. We don't charge anything for that. Hard copies are charged as per the subscription rates. And this is just some data which I thought I will share. Total articles for new journal in 2022 is 143, and we have, yeah, okay, I am almost done. And we have, as you can see, almost 50% rejection rate, and of course the work is going on. Of course, this already I have told, so I will not repeat this, whatever process we follow. And this is our campus. So we have a lot of activities. We have actually one campus in Pusa and another in Satsang Vihar Marg in Delhi. And we have this, time to time we have our Jigyasa project. We have the school children coming to our campus. There's a beautiful fountain there, you can see in the middle. And we have a herbarium also, and a botanical garden with all the trees and all everything labeled, publications and so forth. So that's our institute. So thank you so much. Thank you for your patience.
So we wish you all the best for Indian Journal of Chemistry and new format of Indian Journal of Chemical Technology.
Thank you, sir. Thank you.
So I think it will come very well. So on behalf of organizing team.
Thank you, sir.
So now I would like to invite Dr. Devinder Kumar, who is the professor at Department of Chemistry and Dean Academic Affairs and Dean Faculty of Physical Sciences at Guru Jambeswar University of Science and Technology, Hisar. So without packing, he has a lot of experience, and he has visited abroad several times, and he is a pure academician. So I request him to deliver his talk. No, I will not cut the time. That whatever time I have given, that you have to do. I will not curtail the time.
Here, for whom we are here, right? Even though I thank the organizers as well as Professor Rashtrasant Agarwal for giving me the opportunity to talk here with very few audience. I was listening to the previous speaker from NISPER. Before starting my talk on this topic, I will take less time, not much time, okay, because the previous speakers has spoken a lot, okay, and now it is not the time to grasp all the things, it is difficult to absorb, even for the students and even for the teachers. But for this, about the journals he was talking about, I'm sorry to say that after 59 years, the impact factor of this Indian Journal of Chemistry is 0.4. Highest was 0.6. It is a very sorry state of affair. The government should do it. CSIR should do it. DST should do it. And my suggestion to the Mr. Chairman is that when you write the report for this chemical science section, so you please suggest, it is my suggestion and request that whenever the research project are being awarded, there must be a line added to that, that at least 30% publication should be in Indian journal, which are published by NISPER. With this, I am hopeful that the impact factor will definitely increase. There are journals whose life is only 5 years, 6 years. The impact factor is 4, 5, 3, and we are just lagging too much behind. Maximum impact factor of a journal from this NISPER is only 1.4, and maximum is 1.4, and that of Indian Journal of Chemistry is 0.1. Maximum it went to 0.6. So with this, I request that if you
Definitely, sir, your suggestion is welcome, but you have to change the mindset of the people. Now everybody is going for postdoc when opportunity is there in India. So it is a prolonged problem. It's not one problem. That we should be ready. NISPER has done phenomenally well. Lot of science reporter, everything is coming. It is well accepted. It is the university and professor in place of getting to that predated published journal. Why not to publish here?
Yes.
So that also drive. You are telling right. One of the way is that what you suggested.
Yeah.
But another way is there we have to leave the mansikta of that English mansikta. Dollar dream. So I will publish in outside journal which is having impact factor 0.2 chemical records. But I will not publish in
here. Yes.
That is the mindset, sir.
So anyway, this was my point. Actually, with that lecture, it came to my mind and I shared with you. Okay. Yeah. So, and then, so it is, the title is phenyl iodine 3-diacetate mediated oxidation of 2,2-hydroxyaryl benzoxazoles. You have read it, I think. So there is no need to read this one. So I am skipping this introduction part. I am coming to this reaction. I will try to reduce my time. I don't wish to take much time. This is what the reaction is being previously well studied and reported, where this phenol, substituted phenol on reaction with say IBD, because iodomazine diacetate, say it PIDA, or say it is your IBD. So what you will find here in this one, that here the reaction is now taking place, I think. Which is your laser point? This one?
No, this one.
So reaction, now you can see the formation of product. In this one, the reaction is taking place at this ortho position and this para position. But at this ortho position, the reaction is not taking place. Only where the substance R1 and R2 are there, the reaction is there. You will find the product at this place, and you will find now what happens in this substituted phenol. Firstly, this PIDA react, and then there is nucleophilic attack of the alcohol, and there is a formation of these two products. So with this reaction, I thought, let me try to do some reaction having R1 and R2 in such a way, because these are the three molecules which are bis benzoxazole, and they are naturally occurring. So I thought, let me start with the work on this one, because this is a substituted phenol. Let me take this part and then do the reaction. Okay, so in this one, what happens, now you will find, now I am coming directly to the scheme here. So in this one, firstly, of course, this product is commercially available. Okay, but it was made from this aminophenol and orthohydroxybenzaldehyde to produce this 4. And this 4 on reaction with this PIDA, there are formation of two products. This 5A and 6A, and surprisingly, this 5A was obtained in 60% yield, and this 6A was obtained only in 10% yield. and the equivalent used are your 4 equivalent of this PIDA in this reaction. And this, another thing is that these 2 products can also be obtained from this one. So there are 2 routes where you can either you get these 2 products from this one and or from this one. And now, in order to get these products, firstly, the tetramethoxy, that is this compound, this tetramethoxy, that is cyclohexanone, I'm just giving the mechanism that how it happens, that the substituted phenol where R is equal to the benzoxazole, firstly, this PIDA react in presence of methanol, which is acting as solvent as well as the nucleophile to produce firstly this. And then there is now it enolized, or you can say aromatized here to produce this compound, and then this phenol again react with this PIDA to produce again this compound. It means that 2 times the methanol is being now reacted here to produce this. And now what happens here, and this you can show here, this is this PIDA react here to produce this one. Now here you can show, but you will see there is they don't think of enolization. Okay, anyway, I don't know from here. Anyway, so this lead to finally the formation of this tetramethoxy, this cyclohexanone. So no one has reported that there is a formation of tetrahydroxymethone in this type of reaction where R1 and R2 are here, whatever the kind of substance may be. Okay, so now this actually I took because in audience the students will be there, so I will discuss the NMR, this C13 hydrogen NMR, C13 NMR, and mass, and also the 2D NMR. Okay, but I'll skip this thing. But I have seen in majority of the papers that data is given, that is of hydrogen NMR, C13 NMR, but assignment is not being done. Data is there. Which hydrogen belongs to at which carbon? Okay, and what is the carbon assignment? Nothing is there. In majority of the publications, I don't see in all publications, in majority of the publications. So it means the interpretation is not being done. Whatever they think that the reaction is going in this way, they just think like that. Yes, this. But in that supporting information, assignment is not there. Okay, anyway, I will just keep this, I want to discuss. Which one? No, not for you. and moreover, because why I was discussing about these techniques to use, people, at least at my place, they were wondering how to get the data. Like 1D NMR, your 2D NMR. This one? Okay, so you see this is HSQC. So which hydrogen is attached on which carbon? Very simple 2D NMR, that on one side what you will take here, that this one is your C13 NMR and this is your hydrogen NMR. So now if you look at this one, suppose if I say this peak, that is this one, this contour plot will say, this is the hydrogen. If you just extend this one to this place and then come to this one. So it means that this hydrogen is attached on this carbon. So this is a simple assignment to correlation. We are trying to correlate hydrogen with carbon, that which hydrogen is attached on which carbon. So that we can do. So that correlation spectroscopy is for hydrogen. But this one is HSQC is for hydrogen with carbon. Okay, so head core. Earlier we used to say head core, but nowadays it is your HSQC. Head core and HSQC, they are same. And there is another one that is called HMBC, where what we can do, we can correlate the hydrogen not only attached with that carbon, but extend it up to 3 carbons or 4 carbons. So that also we can establish that which carbon is which. So that we can also do through your 2D NMR. There is 3D NMR also. You might be knowing there is 3D NMR. 3D NMR is used for the analysis of this protein, peptides. Because on one axis there is hydrogen, on another axis there is carbon, on third axis there is nitrogen. So 3D NMR is also there, but for that purpose, you need at least the experience of 1 year for analyzing small molecule like amino acid, dipeptide, tripeptide, and then go up to your polypeptide and proteins. It takes 1 year to analyze 3D NMR for that. And why I was letting you know about this instrumental detecting, because the students actually approach here and there and to get the data. But the data are either they are being delayed or they are not received for one reason or the other. So what I did, in spite of my little background on the research, I'm not too good researcher. I'm just doing some work on like this. What I did, I established a central instrumentation lab, and there I procure, of course, with different funding agencies, NMR, 400 megahertz, LCMS, having this MS up to 4 decimal place, and FESM with EDX, your Raman spectrometer, XRD, DSC, UV visible NIR. So I procured all those equipment. Now I have all the instruments available with me. Okay, this is the X-ray structure of that molecule, which was established, and this is the packing arrangement of that molecule. And now the second molecule, that is the 6A, this 6A, I established here that what is the mechanism of, not established, but that is also the subject to change at any place here. So 5A mechanism was given, but how 6A is obtained? And that is the bicyclo 222 octanol. So this I could see here that there is the formation of this compound. Maybe here due to firstly there is a formation of this compound. That methanol is now this OH attack on this one, and then methanonucleophilic attack this. Then there is a production of this, because in initial reaction there were two products. So one product similar to this. So this actually now undergo 4+2 cycloaddition reaction. These are the same product, this product, and can produce this one. And this, if we change the orientation of this, now if we change the orientation from this to this, there is a formation of this product. But this one is not obtained, this one is obtained. Okay, so this is also established based on your this 1D NMR and 2D NMR. So I am now, you see here that these four, this green, this hydrogens, they are here, 4, and then next you will find these 4 are here. Okay, so we have to establish in such a way that the students have to learn the things in such like this. And now, look at this reaction. I thought, let me change the benzoxazole to benzothiazole. And surprisingly, of course, you will find both the products are obtained, but in previous reaction where it was sulfur, instead of sulfur there was oxygen, this was the major product, okay, and this was the minor. Now it is reverse. This is the major product and this is the very minor. Only 4% yield, and this is 75% yield. We isolated both the product, analyzed. So it means the sulfur is controlling the thing. Just change of oxygen from oxygen to sulfur, it is being controlled here. Okay, now for this one, this product, for this one, particularly this one, 6B, this is a single crystal for this one, and this is the packing arrangement for this one. And now it was extended further. Let us do some more substituent like chloro and bromo. And now when chloro and bromo were just introduced, at which position? At this 5 position. Now in this one, there is a formation of this product, this one as well as this. Only in very less amount, 10%, and this was more than 70%. And I could establish here that this product is obtained by this. This is actually the intermediate for the formation of this product. And in this one, there is another tetramethoxy product, different than that of the earlier reaction. Just by introduction of what? Chloro and bromo. You see that this is also a new product. Not reported. You see in this reaction, at this point, there are 2 ortho position and 1 para position. At this para position, reaction is there. At this ortho, the reaction is being reported, but not at this one. But here I am reporting at this place. So here the tetramethoxy product is different from the earlier product, and this was obtained. And this is what this intermediate for this, because when it is isolated, it was converted into this product. Okay, so this is again the NMR, and now this is the slide where oxygen is now changed to sulfur. I mean benzoxazole to benzothiazole. In this case, the entirely different reaction. So here the reaction is taking place at which, at this place only pure methoxy. It means the sulfur is controlling in a different way. Oxygen is controlling in a different way. But till now we could not establish how it happens. We need some help of computational chemist also in order to know these things. And yes, only then I think we will be able to explain this one. So this was actually all about what I wanted to let you know. And now you'll find here that benzosol substituted phenol undergo dearomatization, leading to the regio and stereoselective synthesis of this tetramethoxycyclohexanone, whereas benzothiazole substituted phenol readily undergo regio and stereoselective dimerization to produce bicyclooctanol. Whereas you will find halogenated, in the case of halogenated, when chloro and bromo are there, they behave differently, leading to another your tetramethoxy, here 2,4,5,6, and it is your 4,4,5,6 tetramethoxycyclohexanone, whereas halogenated, that is 2-hydroxyaryl benzothiazole, afforded only one product. That is, so this means we can say this is stereospecific, not stereoselective. So this is what I could finally make here, that this is what is the substance. I have changed here this R is benzoxazole and benzothiazole, X is equal to your H, bromo and chloro, and when we are doing the reaction in presence of methanol, there is a formation of in the initial reaction, if you remember, that these were the two products. These two products were obtained, but this is not being isolated because this immediately undergo this pericyclic reaction to produce 4+2 cycloaddition reaction to produce this bicyclic product, and now there is a formation of this also. Okay, but this X is OMe only when this X is equal to H. Okay, and then it now when X is equal to OMe, there is a formation of the tetramethoxy product. Whereas in this case, you will find when it is your bromo and chloro, there is only this product. I have written it on this side also. That when we are having R is equal to benzothiazole, X is equal to Cl, you are having the formation of only this. But third product, that is the reaction at third, because it is taking place at 1 and 5, it is also taking a third. So in this file, you will find there is a formation of this. But this is, of course, this is isolated, okay, but this then lead to the formation of a different tetramethoxy product. So these are all analyzed based on the instrumental technique available with us. Okay, and although these product has been submitted for cytotoxicity. Of course, we did this antimicrobial, but I am not discussing this one. Okay, thank you very much.
It's a wonderful lecture, sir. So people who are not here, they have missed a really good thing. And I would take this opportunity to invite you to IICT to deliver a lecture. Yeah. So, Babu, thoda collect kar lena sir ka information. So we have to take him that assignment. So thank you very much, sir, that they missed something. Okay. So in the next opportunity, whenever they will get, it will be very nice. So on behalf of my pleasure to present to you. Besides doing all administration, you are doing good chemistry.
Thank you.
Very good chemistry. Any help you require from IICT, we are there.
Okay, sure, sure. और मैं यही बता दूं, I was in US because of Dr. Dalif. He invited me there. Well, second, I am student of Dr. S.P. Singh. Yes. Third thing, Dr. Randra is my junior. We worked in the same lab.
ये सब लोग का कॉन्फ्रेंस आईआईसीटी में करा
ऐसा ही होता है
ठीक है आपको बुला देंगे ठीक है so today that last speaker today I will like to invite Dr. Bhaskar Chakravarti. He is from the most proud part of our country, that Sikkim Government College, an extension of Sikkim University. He is the Associate Professor and Head of Organic Chemistry, and he was Academic Fellow at Cardiff, UK, and he got the CSIR Best Teacher Award in 2011. He has supervised 7 PhD, 3 scholars are working with him, and he has published so far 72 research papers in peer-reviewed journal. So we are there to listen to you very carefully. So stage is yours, Dr. Chakravarti.
Good evening, one and all, and Happy New Year to all of you. Professor R.D. Kaushik at least could make some time, so I am very much thankful. So much of chemistry today, we all rather we have enriched ourselves. I don't know how much I can contribute to this fraternity in the last form of this lecture form. I am working in Sikkim Government College, which is an extended unit of Sikkim Central University. I have been allotted 5 to 10 minutes. It has been given time. Anyway, so many skips I will be just skipping, and briefly I will tell the work which we are being conducting there. Before I go to the slides, the work which is very much known to the synthetic organic chemists is all about reaction intermediates. It is on nitrones, which is basically formed, everybody is aware of it, from carbonyl compounds and hydroxylamine hydrochlorides. And thereabout, the intermediate in the previous literature has been found that it was trapped with CC double bond and CC triple bond to give us various forms of isoxazolidine and isoxazoline rings, right? Now, during the process, the chemistry is known to us, but in our lab, we have shown some of the methodologies where the application of those cycloadducts as well as in the form of the application of nitrones for variety of new compound synthesis has been conducted. So, that was the main purpose. Now, I am coming to the area where we have just mainly focused on. I am just keeping these things, whatever we have said. So, everybody is aware of these things. So, students are not there, so I am not going to that part. We are using the green chemistry methodologies, and we all are aware of it, why we are using green chemistry methodologies. So, again I am not going to take any kind of extra time for explanation of these things. The main important part which we are conducting in our laboratory is aqueous phase synthesis, ionic liquid mediated reactions, solvent-less reactions, as well as atom efficient reactions. Now, nitrones and cycloadducts, the conventional methodology in any literature you will be finding. One of the most important thing which has been recently being conducted is host-guest interaction with Professor Mahendranath Roy of North Bengal University with beta cyclodextrin, our cycloadduct with host-guest interacted product, and that has been conducted successfully in earlier 2022. This is the new part. Another new part which is there is the mechanochemical synthesis part. That has been conducted when I was in Cardiff University, ball milling methodology, and it has been given excellent result. Those results are beyond comparison with the normal methodologies or normal working procedures for the synthesis of different kind of cycloadducts in the form of isoxazolidine or isoxazoline derivatives. So, these are the few works which has been adopted in the form of green chemistry technology and green chemistry methodologies. I am not going to discuss elaborately all those things because it is now not, it will be well accepted I think by all of us. Peptide synthesis was one of the new feature which was added when the cycloadduct which was synthesized in our laboratory was treated with alpha amino acids in presence of DCC. That was one of the thing. Aziridine derivative was also one of the new kind of synthesis which we did in our laboratory. In the same form, we are coming to some new reactions where carbonyl group is not there, which is the main primary requirement for the synthesis of nitrons, but the precursor is such kind of spaces where the ring can be opened. So, we have used this kind of spaces, followed by we have used synthesis of nitron from other different means, and we have used some basic synthetic applications where aldehydes and ketones can be synthesized using nitrons as an intermediate, which was previously not reported. So, these are the two different kind of synthesis, and then I have mentioned that we have adopted atom efficient methodologies. It is because of the side product which has been the enamine, which has been used as a new dipolophile, and a new kind of spirocycloadduct has been achieved. So, these are the few new techniques which we have adopted in our laboratory. Along with, we have synthesized bis nitrons and bis isoxazoline derivatives. Then we have opened the ON bond of the isoxazoline, and these are the few molecules which we have synthesized newly. And we have done some biological screening with the aid of Jadavpur University's biotechnology department. So, some data are there which I am skipping. These are the antibacterial, antifungal in broad spectrum, yes, data are there. This is the very briefly the summary of the presentation, which is 1,3 dipolar cycloaddition reactions, and based on their applications and some few new methodologies, we have done screening of anti-cancer activities has also been now conducted and is going on. And lastly, we have got the different funding agencies for conducting the research work in our laboratory. So, these are the known funding agencies, everybody is aware of it. These are the different areas where myself and my research group has attended the different conventions and the parts, and these are the areas where different activities from our laboratories has been conducted in recent years. And in fact, this is the laboratory was established in our institution in the college in 1997. So, you may say this is 25th year of the celebration of my laboratory's research work. Yeah, so that part is there. So, finally, I am really thankful, although she is not there, Ranjana madam, for inviting me for delivering this research lecture here, and all the professors and the research scholars, faculty members of this Nagpur University. And it was really very nice place. We have enjoyed yesterday few places, and the Buddhist culture and the sculpture which we have seen, no, is really enriched myself. Yeah, it was really nice. It is different from other states of our country, definitely. So, few research scholars are here, and when I am from Sikkim, definitely I have to show you some glimpses of Sikkim. Sikkim is famous for orchids. So, these are the few different species of the orchids. If you visit Sikkim, please visit our institution, and I will take you these places where you will be enjoying these world famous orchids. This one, and our institution has been upgraded to Sikkim State University. So, now it has been there, and finally, I think we need to have this quote from Madam Carolina, I think. When the world is in trouble, chemistry comes to its rescue. Is given in the Nobel laureate lecture recently, and that is the most attractive lecture quote I have found in recent days. So, this is the thing, and Madam Carolina, this time, yeah, the 3 Nobelists, she is one of them. Click chemistry and bioorthogonal chemistry. Yeah. So, this was the Cardiff University's picture. So, thank you very much.
Very nice lecture.
Yes, sir, I skipped.
Wonderful work being carried out at the Sikkim University, and due to this type of work only your status has been raised to the university. So teachers like you are the real torchbearer of that, and you have been able to attract pharma industry also there. So you
Yes,
have
sir.
done good chemistry there, that's
Yes,
why
sir.
it is becoming a pharma hub there. And I have been to your state, and I have been our now DST Secretary Dr. Srivari Chandrasekhar.
Yeah.
We have started a Northeast program at IICT because this Infosys Award of Dr. Chandrasekhar sir, we brought every year 30 students from Northeast different states. Only they have to pay their travel, coming and going. We give them free accommodation, free training for SRF, JRF exam. Even Chandrasekhar sir promised them that if you want job in industry, job is secure. But during except 1 year of pandemic,
Yeah.
almost 130 students we trained. 112 are in the research. Some of went there and become interpreter in coaching. So all are there at SRF. So all the best, sir. And wherever
Thank you,
you
sir.
need help,
Yes,
we
yes,
are
sir.
there to support Sikkim and all
Definitely.
the Northeast.
Definitely, sir.
Wonderful job done.
Definitely.
So on behalf of the
Madam, please take photograph. Take the mobile.
So on behalf of organizing team,
Yeah.
it's our pleasure to felicitate you
Thank
with
you,
a
sir.
small memento.
Thank you,
Real
sir.
professor lecture were last two. One and two. And somebody has missed something. Okay, so next year, next time.
Definitely, sir. I have skipped many things. There are many internal things like there, like sir wants to share. No, but I don't think chemistry will be now, or it will be digested. So, you know.
Yeah. So on record, I must thank, although this session was a longer session, but we must thank the ISC that organizers and Madam Ranjana Agarwal for giving us the chance for me to become an invited speaker, plus also chairing this session. And this session we have seen, we have gone to all the directions, whether it is organic chemistry, whether it is drug delivery system, it is a biology, whether it is a journal that how to communicate. And in last two presentations, pure hardcore organic chemist, that how organic chemist can learn the art of synthesizing and
Yes.
characterizing the structure, including the materials science, hydrogen generation and energy, co-vaccine, women empowerment. So this was a power pack. Although sir, we are delayed for 1 hour,
Okay.
but it was wonderful. I must thank all my speakers, the organizing team, because I know how much our local organizing team in trouble since last 4 to 5 days. So on behalf of me and our institute, and even I must thank all the local organizing committee, Madam Ranjana Agarwal and whole ISC for giving us the opportunity to share and present our work and share our work to you. Thank you. Thank you all.
Thank you, sir.
It's a time to end the session. I would like to call Dr. Karde sir, Head of Department of Chemistry, for vote of thanks.
So on behalf of Department of Chemistry, we are very much thankful to Dr. Ramanuj Narayan uh, for holding a very long session. It was very difficult session because total 9 speakers were there, and he meticulously managed all that. So thank you very much, sir. Thank you.